And maybe I will share my screen now. How about that? And maybe I will share my screen now. Uh-oh, about that. Hey, Stephanie, I now hear an echo.
Yes, okay. Just want to make sure you heard that, so I knew it was, so it should be fine now. And
sure? Okay.
Everybody got a message that says this meeting is being live streamed?
Yeah, I did, yeah.
Okay, all right.
And I'm, okay, let's see. Why don't we get started here? I'm trying to orient myself. Let's see.
Okay, I'm going to start the recording.
Okay. Anything else, Stephanie, that we need to do?
You are ready to go.
We're ready to go. Okay. Hello, everyone. Welcome to the Paleoclimate Working Group session. I'm welcoming you on behalf of myself, Esther Brady, I'm a co-chair, and Arnie Winguth, who's the other co-chair. And I just put up this slide just to give us a few logistics about the meeting today. I put the agenda in the chat box. Shown here on the right is our NCAR-UCAR code of conduct that we've all agreed to abide by. I want to let you know that we're recording and simulcasting on YouTube this meeting as you accepted to join. Our talks are really short, they're 10 minutes, the slots, and so it'd be great if you could keep your presentations to about 8 minutes so we have time for maybe one question and for some transitioning. And then we can utilize the chat box for discussion and questions. And the speakers can dialogue there with the rest of the participants. Please use the raise your hand button to ask a question. And the chat is going to be saved. All discussions, public and perhaps private, although I haven't found that to be the case, may appear in the saved text file. Please unshare your screen at the end of your talk so we can transition fast, and keep your microphone muted when you're not presenting or asking a question. And then I'd like to let you know that following this meeting, we're going to have an informal meetup networking session. Stephanie, who will be facilitating us behind the scenes here, Stephanie Shearer, she'll leave us at that point. So if you have any, need some troubleshooting done, you can contact Stephanie through the chat, I guess. Okay. All right, so one thing I'd like to make you aware of is Thursday afternoons, alternate Earth sessions. We have a participant today, Colin Goldblatt, a professor at the University of Victoria, who's giving a talk, an invited talk there. And this should be a really interesting session to tune into. So I wanted to make sure that you were aware of this. And we did have a speaker who wasn't able to give their presentation today due to some unforeseen circumstances. So I have a little bit of time, and I thought I would kind of give a brief update on some of the things that we're doing behind the scenes here at NCAR in the Paleoclimate Working Group. So I have a couple of slides here. First, I just want to let you know of what we're working on currently and what we have plans for with our current CSL allocation that started back in November. I did put the link to the CSL proposal at the top of the chat. And if you're curious and want to read a little bit more about what we're doing, in case you're interested in getting involved in some way, you can check out that link and go there and read more about our plans. But so first is the paleo-calibrated CESM2 work that Jean will talk a little bit more about today, but he also gave a talk in the Atmosphere Model Working Group session yesterday. And then we have 2 transient multi-millennial simulations that we are have and will be performing with CESM2 coupled to the CESM2 ice sheet model. The first is the last interglacial climate ice sheet project that we talked a little bit about in our updates. And that is a joint land ice paleoclimate working group project. And then the next is another joint land ice working group project to simulate the transient Holocene starting at 9,000 years ago with the CESM2 ice sheet. We have a control going and we're just about to get a transient run started. We're also starting to work on running or simulating the last glacial maximum with CESM2 coupled to the YOKO 6 middle atmosphere model. And this is something that Jean Zhu has also started working on using the paleo-calibrated MG2 modifications that he made. And we're working on this jointly with the whole atmosphere working group members who are at NCAR. And then lastly, we're doing some idealized meltwater simulation for the Heinrich Stadial 11 event. And that is planned to be about 4,000 years long, but we're at year 1,000 currently. In the future, we want to get going with these high resolution paleoclimates with CESM 1.3, running CAM at the 1/4 degree and the SC dicore with the coupled to the 1 degree pot model. We also are planning to use the CESM2 YOKO 6 configuration for a warm paleoclimate like the Eocene. Marcus Laverstrom is with the land ice working group. We have a project to start a glacial inception simulation. Starting at the end of that transient LIG run. And then later on, towards the end of the allocation, we hope to get started using MON coupled to CAM to run the LGM, which will be a good test for that configuration. And then last, we are still planning to get water isotope tracers in CLM, which is the component currently that it's not configured in at the moment. So we're also working on, and it's taking quite a long time because it's a lot of data to move, but we're migrating our older cases off the HPSS, a tape archive system that's going away at NCAR, to the GLADE campaign storage space, which is disk space. And the HPSS goes away in October. And so and it's very slow to move data off of it, especially old data. So we've been, Betty and I and Nan Rosenblum and Christine Shields have been taking a look at what we have on the HPSS and moving it to campaign space for the community. So this is just a list of what we've been working on so far. We have simulations from earlier PMIP projects, the PMIP2 with the CCSM3 and the PMIP3 with the CCSM4. We have additional simulations that we ran with Paleo Working Group Time, with CCSM3 and CCSM4. There's a number of last interglacial runs through the last interglacial. The CCSM3, there's some meltwater sensitivity runs, starting from a base state of the last glacial maximum, and then a mid-Holocene case for the 8.2K event. And then we have some community collections that have been available on the NCAR Climate Data Gateway that were on the tape archive. And we're trying to get those also off of the HPSS so that we can host them on campaign space and continue to host them for the community. So there's the CESM1 collections of idealized forescenes from Michael Erb's sensitivity runs, and then Clay Tabor's end member foreseen simulations with the isotope-enabled CESM 1.2. And then there are the CCSM3 and the new CESM 1.3 simulations of the deglacial period with the TRACE, the Lewin Betty's TRACE project. So the CESM 1.3 version was run with the isotope-enabled models. And then we have CESM 1 collections for the last millennium ensemble, and then the mid-Pliocene sensitivity runs that Ren Feng has contributed many sensitivity runs to. She ran most of these runs. And I think we will have a couple minutes here for questions before we get started at 8:45. So let me stop my share. Does anyone have any questions about any of that or anything having to do with the Paleoclimate Working Group that I can address in the next couple minutes? Oh, Andreas. Sorry.
Hi, no
Hi, Andreas. Sorry, I guess I'm not quick to see your hand raised, so that could be an issue.
I was just wondering, are there plans to have like a carbon cycle coupled CESM version for, you know, carbon cycle applications ready?
Well, in my update talk, I mentioned some work that's going on outside to put the carbon isotope tracers in CAM. That's being done by the University of Bern researchers Alto Bikisi and Fortunat Yost. And we hope to get those into CAM. And then at that point, I believe it would mostly be possible to get the coupled carbon cycle going. I'm not sure if it's in the runoff model yet. I think they're still potentially using data sets to prescribe the carbon isotope fluxes to the ocean and the carbon fluxes to the ocean as well. So that would be one remaining model that I'm aware of that potentially wouldn't have them for a full coupled system. But yeah, I think it's something that it's in our research priorities for you know, down into the future. And I did give, well, I can show it. Let me show. I don't know if we have time. No, we don't. But anyway, it is something that that is in our mind for the future, but I don't think we're quite there yet. With the work that we need to bring in from the external collaborators. So, yeah.
Okay.
So is our first speaker is Jen Kay. Is Jen Kay here? Yes. Jen Kay is a professor at the University of Colorado here in Boulder. And she is speaking on what causes 20% more 2 times CO2 global warming than a 1/2 times CO2 global cooling in the community Earth system model.
Yeah, good morning. Thanks for the opportunity to speak briefly about this work that I've done in collaboration with the folks listed on the slide. I want to especially call out Jason Chalmers, who's now a graduate student at the University of California, Santa Barbara, who did much of this work during the pandemic last summer. And so really kudos to him for getting this project really off the ground. And the question is really big. Why do the climate and cloud responses to idealized greenhouse warming and cooling differ? And the reason we ask this question is because it's a fun big picture question to work on with an undergraduate student over the summer for sure, but also because these idealized greenhouse warming and cooling experiments have really been called out as being important as a constraint on equilibrium climate sensitivity. In particular, the amount of cooling that you get could be a constraint on how high equilibrium climate sensitivity might go. And so these experiments are rather idealized, so they're a little easier to understand than, for example, the last glacial maximum, where a lot more things have changed. So just quickly to introduce the experiments, we basically have run the fully coupled 1 degree CESM1 version for 150 years. This is just a time series of the energy imbalance and the surface temperature change. And what we see is about 20% more warming in response to the carbon dioxide doubling than we saw in response to the halving of the carbon dioxide concentrations. So this was kind of a first order result that's kind of interesting to see. A lot of this response happens in the first couple of decades. That's consistent with sort of these fast timescales that are important. And then this long tail, you can see these simulations are way out of equilibrium. They've only been run for 150 years. So the ocean circulation is not quite, and ocean uptake is not quite equilibrated. So really basic, why are we seeing more global warming than global cooling? We diagnosed the effective radiative forcing, and we found that is about 10% larger for a carbon dioxide doubling than for a carbon dioxide halving in CESM1. So this is part of the reason why it warms more than it cools. We also looked at radiative feedbacks globally, and unsurprisingly, cloud feedbacks end up being very important for some of the differences that we're seeing under warming and cooling, and in particular the shortwave cloud feedback being important for more warming than cooling, with some compensation from the lapse rate feedback. So if we look at maps of what this looks like, so here's just the warming and the cooling, we see a lot of similarities in the patterns, stronger responses at high latitudes and over land. Even some of the patterns in the tropical oceans look sort of similar when you have and when you cool, just opposite in sign. So if we look at the difference, and then on the bottom, the pattern difference, which is just normalized by the response, globally response, we can see, some interesting features that relate to why there's this asymmetry. We see differences in the high latitudes, of course, where sea ice has been lost and gained, so strong differences associated with that. But then also some other more intriguing differences. For example, more warming over land than cooling over land. So not entirely sure what's behind that. And then also some pattern differences, especially in the tropical Pacific. We can see this interesting cooling feature off the coast of North America that's associated with the cloud feedback difference, as we'll see. So we looked at the maps of the radiative feedbacks to help explain these surface pattern differences. And so you'll probably be most familiar with what the feedbacks look like in response to a carbon dioxide doubling. Here we just also show the difference between the doubling and the halving. And you can see, at the high latitudes, it's these coupled surface albedo and lapse rate feedbacks that are really amplifying the surface temperature response associated with sea ice loss. And then the cloud feedback difference, more positive cloud feedback over much of the globe. There is an exception, again, off the coast of North America here, where we actually see an opposite sign, where so the cooling the feedback is somewhat stronger. So yeah, just some notes. Also important to note that the Southern Ocean and the mid-latitudes and the land cloud feedbacks appear more positive under doubling than under halving. In the tropical Pacific, we see many similarities associated with the surface wind response that look similar under doubling and halving. But when we look at the pattern difference between doubling and halving, we see a strong role for the cloud feedbacks. In particular, the cloud feedbacks are important for sort of amplifying this stronger warming in the Western tropical Pacific, and then for the sort of rich spatial structure in the Eastern tropical Pacific, which tends to be somewhat delayed in its response due to the ocean circulation. But this pattern is strongly shaped by the cloud feedbacks in this region. So we can look at this kind of slow timescale response. So here we're just looking at how things are evolving over the sort of the last 50 years of these simulations. So it's not particularly slow for the Paleoclimate Working Group, but it is a slow timescale in these particular experiments. And we see some really interesting contrasts. For example, over the Southern Ocean, where warming tends to be somewhat delayed. So we have a relatively large slow fraction. Under halving, the cooling actually appears to be relatively fast, and some of that could be due to the advancing sea ice edge, but also differences in ocean stratification playing a role there. We see that, when we look at the magnitude of the slow change, though, a lot of similarities to sort of the total change that we're seeing over these experiments, with sort of the largest amplitudes of the slow change being in the high northern latitudes. So the ocean dynamics and the cloud feedbacks are really important for explaining the tropical SST response time evolution. And maybe just for the sake of time, I'm just going to skip through this, but just to say that the cloud feedbacks, again, are playing a really important role in shaping these both slow and fast timescales in our experiments. Okay, so now moving on to something kind of fun. Actually, this month's Nature Climate Change cover features cloud feedbacks. Whether clouds will warm or cool the planet under climate change is, of course, very uncertain. And there's two studies in this issue that are quite relevant to cloud feedbacks. One of them in particular I want to call out has to do with how warm and cold clouds precipitate. And what this study found, Molmeshat et al., is that basically we're missing a change in precipitation efficiency, and that's sort of a missing negative feedback. And so it really calls into question, for example, these really large equilibrium climate sensitivities that we're seeing in the latest generation of CMIP6 models, including CESM2. And says these are not the final word on this. There's plenty of reasons to think that there are other processes that are quite relevant that could lead to negative feedbacks that would make these equilibrium climate sensitivity values come down. So we were interested in repeating our experiments without the cloud feedbacks because cloud feedbacks tend to be a real source of confusion and just a lot of different things going on.
Oh, 1 more minute.
Yeah, I'll be pretty quick here. So we disabled the cloud radiative feedbacks. Just to point out that even after we disable the cloud radiative feedbacks, we still have 20% more global warming than global cooling. So there's some interesting compensation going on there, but that number seems to be rather robust globally. And that we see differences in sort of this cloud influence, which is the difference between the control simulations and the cloud block simulations. And for example, clouds are amplifying responses at high latitudes when they're enabled, whereas we don't see any evidence for that when we look at these diagnostic cloud feedbacks. And finally, I think it's really interesting that this cloud influence affects the response magnitude more than the response pattern. So it really emphasizes that clouds are coupled to the circulation, to other feedbacks. And so just diagnosing cloud radiative feedbacks offline after the fact gives you a really different story than what you learn when you actively disable them in the model.
1 minute.
So I'll just leave this summary slide here. I don't want to go over on our very first talk. I have 8:55, so I think I'm all on time.
Thank you, Jen. We might have questions in the chat, I think, just to keep us on time. That was really interesting.
I'm happy to just answer questions in the chat. And also this paper has been submitted to Journal of Climate. So if you're interested in a copy of it, I'm happy to share.
Oh, great. That'd be wonderful. So our next speaker is Marcus YOKO, a professor at the Niels Bohr Institute.
Yeah, hi everybody, and thank you for your time. Yeah, I'll show some work that I've been doing with colleagues here at the Niels Bohr Institute in Copenhagen and with people from the University of Tasmania. We're looking at carbon fluxes in CESM. So what we want to understand are the millennial scale CO2 fluctuations that we see in the ice core record. And I'll show some parts of the ice core record here. Shown here are 50,000 years of temperature in blue. You see every couple of thousand years we have very strong warming. These are the Dansker-Oeschger events, followed by a slight cooling. Preceding the warming is what is called a stadial. So those are the cold periods within the glacials. And associated with these stadials, we have Antarctic warming. So it's shown here. And so this has been well explored now, also with the use of CCSM. And what is less understood, though, is the connection between these signals here and the CO2 record. So we see that whenever there's a stadial and the temperature is increasing in Antarctica, we see an increase in the CO2. This gave rise to a lot of hypotheses that CO2 is driven, or the CO2 signal is driven by the warming in Antarctica. Although we should note that the increase in CO2 here lasts longer than the increase in temperature. So the cooling starts and then the CO2 tends to increase. What we did is we used CCSM. It's this T31/3 setup. So we get something like 100 years per day on our cluster. It is a setup. Guido Vettoretti has published much of this on the physical component. What we did is we added biogeochemistry to this physical setup. Yeah, so I won't have time to go through all the details, but we use this setup, and first of all, we want to check if it reproduces the observations. And this is shown here in the upper left corner. We have here like a 3,000-year segment of a 9,000-year integration that we did. It features two stadials. We look here at the black line, it shows the temperature over Greenland. We see there's a very rapid warming, and like in the observations, it has an amplitude of some 15 degrees Celsius. During the stadials, the Antarctic temperature increases. I hope you can see my arrow. It's a bit small, I should have increased it. But the blue line shows the temperature increase in Antarctica. Again, in line with the observations. It also is about a 100-year time lag between the onset of the interstadial and the cooling in Antarctica, which is very similar to the records inferred from volcano records recently. Now, the really exciting thing is then the carbon signal here shown in red. As soon as the stadial begins, we get an increase in atmospheric CO2 concentration of about 1 ppm per 100 years. So this is the same rate that we have in the observations. Our stadials are rather short. In this particular experiment, it's only like 300-400 years. So we get a CO2 response of 3 to 4 ppm, which is on the lower end. But again, our stadials are a bit shorter. Associated with these stadials is an AMOC response, which is shown here, which has been documented before. And on the lower left, you see the temperature response in color. An important response is the precipitation response. So there are large precipitation shifts associated with the stadials, which is shown here in red. And one important part is the drying over Africa, for example. And there are slight changes in the wind stress over the Southern Ocean. There's about a 5% reduction in general. And this helps us then to explain the stadial anomalies of the surface to air carbon fluxes, which are shown here on the right side. Positive numbers here show an increase of atmospheric CO2. And one thing you notice is the patchiness of the response. So you have pluses and minuses all across the board, which makes it a bit challenging to come up with a good way to structure this problem. But what we decided to do is to lock together the North Pacific and North Atlantic response together. So they're highly correlated to the AMOC. The basic effects here are you have an increased sea ice cover, which reduces the uptake. We have a cooling here, which increases the uptake. So those are compensating effects on both. Also, reduction of the AMOC is, Andreas's earlier study showed this as well, associated with the collapse of the marine productivity here, because the nutrients are just simply lacking. So those are the three major responses in the Northern Hemisphere. In the Southern Hemisphere, the total response is a bit smaller. And again, we have a compensating effect of basically less subduction of carbon-rich water here in the Southern Ocean, which gives rise to an atmospheric CO2 signal. And then we have less outgassing here in the tropical Pacific mostly, but throughout the tropical ocean. So we locked this together then in three different components. We have a land component caused here by the drying, and the two different ocean components. And we can integrate these carbon flux anomalies to try to explain what explains the CO2 response that we see. Again, these black lines here indicate the Dansker-Oeschger events, or the sudden warming in Greenland. Preceded by them are the stadials. And we see that most of the stadial response in CO2 comes from the land. There's a little contribution of the Northern Hemisphere, of the North Atlantic and the North Pacific. And the Southern Ocean and the tropics act to counterbalance this. Now, the interesting part here is this large overshoot here, that as soon as the Northern Hemisphere warms again, there's a massive outgassing of CO2, which then explains the delayed response that we saw earlier, that the CO2 is rising even though the temperature has equilibrated yet, or has returned to a normal state. Our signals are a bit smaller. I think we have the right increase of CO2 and the right rates, but our Dansker-Oeschger events are a bit short. So we helped us out with some housing. And shown here is the CO2 response during the Dansker-Oeschger events. The blue one is the one that we discussed before. We have a 3 to 4 ppm increase. We can prolong the stadials by hosing. So in the middle of the stadials, we simulate our Heinrich events by adding slight hosing to the North Atlantic. This prolongs the stadials for another 800 years, which gives us a larger CO2 signal. And the nice thing is that the rate of CO2 increase does not change. And this is very much in line with observations where Heinrich stadials and normal stadials do not have a different increase in CO2. One third experiment we did is we reduced the iron deposition, or the alloional flux of iron. Some of the ideas related to the Southern Ocean suggest that since it's warmer, there should be less dust deposition in the Southern Ocean, which would reduce the productivity and increase the atmospheric CO2 concentration. This is something we investigate here with our reduced iron flux experiment.
8 minutes, 2 minutes left.
I'm sorry?
8 minutes, 2 minutes left.
Okay, we can then look at the various regions again, and we see, without going into the details, that the biggest changes happen really in the North Atlantic area and the North Pacific area here. We both locked them together as under AMOC. The blue here shows an increase or reduced uptake in the North Atlantic and Pacific, which what we expect through a hosing experiment. But one of the surprising things is that the biggest signal that we get from the reduced iron experiment does not happen in the Southern Ocean. There's very little response in the Southern Ocean, but we do get this in the North Pacific. And it helps to look at the spatial pattern of our differences. So there's a difference in the stadial carbon fluxes between iron and hose. The blue line overlain here shows the pattern of the aeolian dust deposition. And we see in areas where we have large dust deposition, we do have indeed a stronger response. But wherever we have increased or reduced uptake of iron, we also have reduced outgassing. So there are large compensating effects at work that we get very little net contribution from the Southern Ocean and the tropics again. But the main net contribution happens to be from the North Pacific. So the nice thing is we have now an LGM configuration with a full carbon cycle and a realistic CO2. It realistically represents Dansker-Oeschger oscillations in their carbon input, so we can now look at the mechanisms behind the various carbon signals. We find the biggest signals due to land. many of the ocean processes compensate each other, but in general, we find that the Southern Ocean is not an important contributor to the CO2 fluctuations, with or without iron, independent of this. Yeah, thank you.
Thank you, Marcus. That was very interesting. I don't think we have time for questions. They'll have to be done in the chat. We should get going with our next speaker, Ren Feng, an assistant professor at the University of Connecticut.
Hi, I'll get started. Thanks everyone for joining today, and thank you to Esther and Arnie for organizing this. So I was set out to talk about the source for the enhanced Earth system sensitivity in the CESM2, but I end up having more questions than answers that I have. So I thought I would share with you what I'm working on and what are the directions I'm thinking about going with this today. Before I start talking about the Earth system sensitivity, I just want to remind everybody about the definitions and distinctions between the equilibrium climate sensitivity and Earth system sensitivity. So equilibrium climate sensitivity, this is the ECS that we're most familiar with. This is the global mean surface warming, air warming to a doubling of CO2. Usually it was calculated by holding the ice sheet vegetation atmosphere composition as prescribed and using the step ocean model. So the ocean circulation is also assumed to be constant. So on this timescale chart made a couple years ago in the Pages News by Gavin Schmidt. So ECS incorporate feedbacks happening from decades to maybe up to a century or so. But when we're really looking at paleoclimate timescale, we're dealing with Earth system sensitivity. This is the warming, the amount of surface warming by incorporating the long-term feedbacks. So those long-term feedbacks include changes in biome distribution, 3D ocean circulation, ice sheet. So they're happening more on the timescale of century to millennial. I want to show the results from Pleißing. This is time period about, especially the mid-Pleißing. This is time period about 3 to 3.3 million years ago, when the CO2 is around present day, the 400 ppm level. And this is the last time the Earth has seen this level of CO2. There is a international modeling project going on trying to simulate this time period. It's called Pleißing Model Intercomparison Project, and we're in the phase 2 of the project. To the top here shows what are the best estimates for the biome and ice sheet distributions for this time interval. And I want to highlight a couple places. This is what the Greenland ice sheet look like during this time. It's very much limited to the eastern side of the island. And this is what the Antarctic ice sheet look like. So you see the loss, the massive loss of Western Antarctic ice sheet. And generally you see the northward shift in biome types. The blue color here shows the Arctic boreal forest. So when models are prescribed with CO2 and with those biome distributions, surprisingly, not just that they simulate, or not that just that the model have different ECS, but they also shows different amount of amplification of warming due to prescribed vegetation ice sheet. So due to the radiative perturbations from those slow responding systems. This column shows the ESS to ECS ratio, which quantifies the warming amplification in those models due to vegetation ice sheet. And you can see it varies from not much in some models to a whole bunch in some other simulations. And it's uncorrelated with ECS. I set up a series of simulations to look at What if we just look at one aspect of changes in forcing conditions from vegetation combined with ice sheets, so this long-term Earth system feedback, or just the CO2, or just the geography and topography changes? And surprisingly, the vegetation ice sheet actually contributes the most warming in the mid-Pliocene simulations. The good news is geography and topography has very little effect. So that reduces the complexity a little bit. And this warming primarily happens in the high latitude, in the Arctic, in the Canadian Arctic, Greenland, and as well as the Western Antarctic. It also has some pretty unique continental warming pattern going on across Eurasia continent and North Africa. If we look at precipitation, the vegetation ice sheet forcing actually has really strong precipitation response, especially compared to CO2 and geography and topography. And there's a really strong response in the northern subtropics from Sahel to the Southeast Asia. We're actually analyzing those results in conjunction with the rest of the Paleoclimate models. And we're having a paper in review discussing this response, because this is actually seen in the proxy records. So proxy records can actually validate this response. So we're curious, so how much radiative perturbations we're actually getting from those different forcing conditions. And similar to what Jen's talk has shown, I did a series of prescribed SST and sea ice experiment to constrain this effective radiative forcing. So this is top of the troposphere radiative perturbation introduced by forcing agent. So ERF does include rapid adjustment from like water vapor, depth rate happening at weeks or months, or even the first few years, and clouds. And a trick is when we do the prescribed SST and CI simulations, we did see there is a surface temperature response. So we do have to, which compensate the radiative forcing. So we do have to adjust for that. And this has been done in the radiative forcing map for CMAP 6, and as well as in John's paper, which did it for the LGM. Just to see how much temperature compensation we're looking at from those runs. From CO2, this is very little, about 1.1 degrees, and prescribed geography topography has a slight cooling effect because there is a little bit of Bering Strait closure, land exposure, and there's a bit of shelf, tropical thunder shelf, Indonesian sea shelf shoring. For vegetation ice sheet, the warming is a little bigger. And combined geography vegetation, again, there's a little warming. If you look at ERF, this is unadjusted for CO2, it's about 2 watts per meter square, 1.96. For geography and topography, it's about minus 0.1. For vegetation ice sheet, it's 1.3 watts per meter square, and the combined geography and vegetation ice sheet is about 1.2.
8 minutes.
Okay. Yeah, I'm almost done. So if we, I did the simplest adjustment using the amount of forcing from a doubling of CO2 divided by the equilibrium climate sensitivity from Andrew Gettleman's paper. Numbers are from Andrew Gettleman's paper. And for CO2, this is after the adjustment, it's about 2.04 watts per meter square. This is I would say consistent with this radiative forcing map estimate for 1.4 times CO2, 1.54 times is 397 ppm, while we're having 400 ppm, right? For geography topography, this is about minus 0.21 watts per meter squared. So for the large part, this is negligible. For vegetation ice sheet, this is about 1.51 watts per meter squared. So here are some unanswered questions that I'm really interested in exploring at the moment. So what is the source for this 1.51 watts per meter square ERF from vegetation ice sheet changes? Is it rapid adjustment of albedo, water vapor, clouds? And how dependent is this estimate on model versions? I'm also working on setting up CCSM4 or CAM4 for this. And why is this forcing so effective? I did a calculation of efficacy for the vegetation ice sheet forcing. It's 40% more effective than CO2. So that's kind of interesting to me. And perhaps we could call the paleo radiative forcing MIP to really help understand those paleoclimate simulations among multiple models. Yeah, so that's all I have. Thanks for your attention. And I will answer any questions if you have them later in the discussion. All right. Thank you.
Thank you. Thank you, Ren. Great talk. And I already see a question in the chat, and I think we will need to move on to our next speaker. So thank you. Great idea about the RF MIP. Okay, our next speaker is Zhan Zhu, project scientist here at NCAR, and he is speaking on an LGM calibrated CESM2 for paleoclimate studies.
Okay, thank you, Esther. Can you hear me okay? Okay, I will get started. So I'm Zhan Zhu. I will share you the recent research we have been doing. It's to develop a paleo-calibrated configuration of CESM2 CAM6. So many of you may know that in a recent study, we performed LGM simulation using the CESM2 CAM6. What we found was that the simulated LGM global cooling is close to 12 degrees C. And it is way outside the proxy suggested range. That's the latest Tierney et al. 2020 estimation. And based on that, we concluded the high ECS of CESM2 is very likely unrealistic. And this is not ideal. It prevented us from doing exciting research using the new capabilities of CESM2. So today I will show you a new configuration with some minor modifications in cloud microphysics. We call it paleo-calibrated configuration. You see that we have overall a realistic LGM simulation and a much lower equilibrium climate sensitivity. So the first key ingredient of this paleo configuration is to remove an inappropriate limiter, which is called Ni max. So basically, Ni max sets the maximum cloud ice number. It was designed to work with the older ice nucleation scheme with a longer time step, but it was not modified accordingly when they developed the new schemes. Therefore, we need to explore its impact on climate sensitivity. So the basic process level understanding is that when you remove this limiter, you have a higher cloud ice number and a more cloud ice mass, which implies a more negative cloud phase and a lifetime feedback. So overall weaker cloud feedback, therefore a smaller temperature response. The second key ingredient is to perform substepping in the microphysics scheme. The motivation is twofold. Firstly, when you remove this Ni max limiter, the cloud ice number grows to value that are unrealistic. So when you increase time step, it improves the simulation of the cloud ice number. Secondly, it's motivated by this paper. Basically, they show that MG2 contains several processes that are poorly resolved at a default time step of 300 seconds. And we found that when you shortening the macrophysical time step, you have an overall weaker cloud feedback that also helps in giving us this overall realistic LGM simulation. And we also did extensive exploration, and we found that 8 sub-step is sufficient for a converging solution in cloud feedback. So this figure shows the global mean LGM cooling in this paleo-calibrated configuration. Now the simulation, we have 500 years. It's marginally too cold, but we think this is overall acceptable. And this is certainly a huge improvement over the default CESM2 Chem6 configuration. And with this configuration, we can perform DAG simulation to quantify the ECS. This figure shows a Gregory plot. You see that we estimate an ECS around 4K. That's much lower than the default CESM2 Chem6 configuration. I also quantified the aerosol cloud interaction, which is 20% weaker. The right figure shows the global warming in the historical period. The blue is our paleo-calibrated configuration. And you'll see that overall, it well captures the 20th century warming, and its performance is as good as the other CESM2 Chem6 simulations. We think what is going on is like this. So in this paleo-calibrated configuration, we have less greenhouse gas induced global warming, at the same time, less aerosol induced global cooling. Because of this cancellation, we still get overall realistic 20th century warming. And these plots show the LGM cooling in surface temperature compared with the compilation in Tierney 2020. This is CESM2 paleo-calibrated configuration and CESM1. And you see that this is certainly much warmer than CESM2 and is closer to CESM1. But there are some differences which are worth further looking into, for example, over the tropics. In the table, I'm listing the root mean squared error in different simulations compared with different proxies. So it's big improvement you see over the CESM2, but it still is not as good as CESM1. So this plot shows power spectrum of ENSO. The black line is observation, and the red is default configuration pre-industrial simulation. You see that the model overestimates the ENSO variability. And the blue is our paleo-calibrated pre-industrial simulation. And you see that we have a somewhat improvement in terms of the interannual variability. The green is the paleo-calibrated LGM simulation. So consistent with what we had in CESM1. So we still see this reduction in ENSO variability in the LGM climate. Oh, so here is a quick summary. We have developed this paleo-calibrated CESM2 Chem6. It's very important that we still use most of all the advanced Chem6 physics in this configuration. And this configuration simulates realistic LGM, realistic 20th century warming, has a low ECS with weaker cloud feedback. And with this configuration, we planned some community research. For example, we want to explore the post-warm climates, whether we see similar improvement in simulation of eocene or miocene. And we are working on LGM simulation using the high top CESM2 YOKO with those modifications. And also we are interested in exploring the LGM dust forcing and the interaction with clouds. Thank you for your attention, and I'm happy to take questions.
Thank you, John. Very interesting talk. And let's see, do we have time, Arnie, for, yeah, I think we
Yes, we
have
do
time
have
for maybe
time for
one.
questions, yeah.
Yeah. Anyone have a live question? Raise hand. If not.
Okay.
Oh, got a
The
question.
resolution is 2-degree atmosphere because it's cheaper to run. And we expect similar behavior in FV1, but that need to be explored. Thanks for the question.
Yeah. Should we move on with our next speaker?
Yes.
Oh, see, okay. Any other questions can be asked in the chat. We have a good conversation going on there. Okay, our next speaker is Yiling Huo from at the University of Toronto. Yiling is a student there. And let's see, you are giving it live. Yes, okay.
Okay, thank you for the introduction. I'm Yiling, and so today my talk will be about the dynamically downscaled simulations we did in our group to study the mid-Holocene monsoon in South and Southeast Asia, and also to investigate the influence, the teleconnections between the Green Sahara and the Asian monsoon system. So generally, proxy data shows that the mid-Holocene was generally warmer than today during summer and cooler in winter due to the different Earth orbital parameters from today, and the complex orography of South and Southeast Asia renders the regional climate complex. And here we used we constructed a series of regional climate simulations using dynamic downscaling to downscale global mid-Holocene simulations. We have also taken care to incorporate the Green Sahara boundary conditions to investigate the interactions between the vegetations over North Africa and the Asian monsoon system. Okay, so the regional coupled model system here consists of a regional climate model, the WRF model, and the 3D ocean model, and our GCM, which is the University of Toronto version of the CESM4. And the WRF model we use is the version 4.1 at 30 kilometer resolution. The WRF domain is the shaded area shown here. And we also use the 4 different cumulus parameterization schemes to estimate the uncertainties associated with different choice of cumulus schemes. And the ocean model was run at 0.2 degree. The ocean domain is the white rectangular here, covers most of the ocean areas in the WRF domain. And the coupled WRF-Croco model is driven by 3 different GCM simulations, 1 for the pre-industrial and 2 for the mid-Holocene. And the 2 mid-Holocene simulations, one of them is called reference mid-Holocene. It used the same vegetation distribution as the pre-industrial, and the other one is called MHGS. It incorporates the Green Sahara boundary conditions, meaning it includes a vegetated North Africa. Oh, yeah, North Africa. Okay. So let's first look at the temperature anomalies during the mid-Holocene here. So this figure shows the SST and the continental temperature changes in the GCM and in our downscaled simulation. The SST distribution is pretty similar, except that over around the southern tip of India, our regional ocean model simulates warmer anomaly, while as the GCM simulates cold city anomalies over the entire ocean domain. And over the land, during mid-Holocene, the temperature is actually warmer by up to 2 degrees northward of the Tibetan Plateau, and the largest warming center occurs around the 40 degrees. And the intensity and spatial extent of this warming center is larger in the downscale simulations than the GCM. And over South Asia, we see a small cooling, and over Southeast Asia, we see actually small opposite temperature anomalies in Western and Eastern regions. As a result, the land sea thermal contrast increases due to the spatially averaged increase in JJS temperature over land and decrease over in SST, which intensify the moisture transport towards land. And yeah, okay. So now let's look at the annual mean precipitation changes in the reference mid-Holocene simulation. Most of the Southeast Asia actually experience wetter climate compared to the pre-industrial, especially over the northern part. And the GCM simulates drying over the eastern Himalayas and southern India, whereas the downscale simulation shows an increase in annual rainfall compared to proxy data, compared to two pollen-based reconstructions here showing circles and diamonds. And overall, there is qualitative agreement with reconstructions with weather conditions in northern region of Southeast Asia and along the Himalayas. And however, they disagree with the reconstructions in Eastern Tibetan Plateau and Southeast China and over the regions north of the Tibetan Plateau. And overall, the downscale simulation displays a slightly greater similarity in pattern to reconstructions than the GCM. In order to quantify this fit to reconstructions, we used this mean relative error calculated using this formula here. And considering all the points with prox data in the WRF domain, dynamical downscaling reduced the MRE by about 10%. And since both model fails to capture the right sign of precipitation anomaly 4 points north of the 40 degrees. So if we only consider points that south of the 40 degrees, the MRE of the downscale simulation is actually about 30% smaller than the GCM. And the other proxy data, however, suggests much larger precipitation enhancement, and therefore is less consistent with both models. And the JJS, the summer precipitation anomaly pattern is pretty similar to that of the annual mean, except that the increased amplitude is greater, and that also contributes to an increase in cloudiness and evaporation, which may explain the lower temperature over South Asia and Southeast Asia we seen before. And if these two figures shows the annual cycle of precipitation over South Asia and Southeast Asia, and the precipitation during the early stage in June here, early stage of the monsoon season in June here is actually weaker, which suggests that the monsoon actually starts later in mid-Holocene than in the pre-industrial, and also the maximal precipitation increase over these two regions occurs at the end of the monsoon season in September, and also there's small precipitation increase in October, suggests that the withdrawal of the summer monsoon is postponed. And finally, all of these increased monsoon changes discussed above are stronger in the downscale simulations than in the GCM. Okay, now let's then look at the impacts of the Green Sahara boundary conditions. So first, let's look at the temperature changes. So the inclusion of Green Sahara surface boundary conditions leads to an enhanced JJS temperature anomaly over the majority of the WRF domain, and with the largest increase over the Tibetan Plateau and the East Asia. So this one shows the difference between these two mid-Holocene simulations. And the JJS
8 minutes.
Oh,
Yeah,
okay.
2 minutes ago.
Yeah, and compared to the reference compared to the reference mid-Holocene simulation, the SST is actually warmer in the MHGS simulation, and this favors more evaporation of the ocean and thus contributing to the monsoon precipitation increase. So now let's look at the annual precipitation anomaly in the MHGS simulation. So inclusion of Green Sahara significantly reinforced the precipitation anomaly over South Asia and South and Southeast Asia, and the increase is particularly large over the northern regions, and it also enhanced the precipitation along the Himalayas, the Tibetan Plateau, and the northern regions, North China, and the regions north of the Tibetan Plateau, and thus significantly improving the proxy data comparison. And it actually inclusion of Green Sahara leads to about 10% reduction in the MRE. Yeah, okay. Let's jump to the conclusions. Okay, so we constructed a series of regional climate simulations using the coupled Wolf-Kraucke model driven by the output from the GCM, UFT CESM4, and we also incorporate a set of downscale simulations to include the Green Sahara boundary conditions to access the remote response of the South and Southeast Asian monsoon system to the greening of the Sahara. Compared to the pre-industrial, the reference mid-Holocene simulation, it shows a strengthened summer monsoon intensity over both South and Southeast Asia, especially over the northern region, and a late monsoon onset and a delay in the monsoon withdrawal over both regions are also found. And overall, the WRF results are in better agreement with proxy data and the GCM. Greening of the Sahara also amplifies the response of the two monsoon systems to the, and leads to a further increase in the mid-Holocene monsoon precipitation. And model data comparison also shows significant improvements in simulating precipitation, especially of the Tibetan Plateau and the northern regions. And these results emphasize the importance of high resolution modeling over regions with complex land surface and highlight the climate sensitivity of Saharan vegetation changes, the ocean atmosphere teleconnections on the Asian monsoon system. Yeah, that's all. Thank you, everyone. And yeah.
Thank you.
Thank you. Thank you, Yuling. Yeah, your last statement drives home the point that we need to do more high resolution paleoclimate modeling. Yeah. Thank you. I think we'll have to take questions in the chat.
Sure.
And move on to our next speaker, William Rush. A PhD student at UC Santa Cruz. He's speaking today on regional variability of the South Asian monsoon through the PETM.
Great, thank you. And yeah, it's a great talk to follow up on that previous one, looking more at high resolution models of the South Asian monsoon. Thanks for giving me the opportunity to present on this. This is a side project I've been working on for a couple months now. And I like to start out all of my talks talking about like my motivations for doing this sort of thing. The South Asian monsoon supplies 80% of the water supply in South Asia, which is the principal supply for well over 1 billion people. It's of significant importance to the agriculture industry and hydropower generation of the region. And it's hypothesized that changes in the land sea temperature gradients due to anthropogenic climate change have the potential to weaken the strength of this monsoon. So I'm going to be going a bit further back in time than our previous talk, looking at the PETM, and this is the world of the PETM. And although we have a slightly different continental configuration than the current day, particularly in that the Indian subcontinent had not yet reached South Asia, we can still use this to draw some parallels to modern day warming. What's particularly interesting about this is in the past few years, there have been several studies that have come out looking at these PETM sections in the region of the Himalayas. And in particular, even though that these are in close proximity today, they can provide us with insight into hydroclimate changes that happened fairly separate from each other at this point in time, namely on the northern and southern Tethys. So I have two locations I'm going to be talking about today. On the northern Tethys, I'm going to be referring to this as Tibet, and the southern Tethys, I'm going to be referring to this as India in my model output. So to describe these changes that have been taking place, in the northern Tethys, this was around 15 to 20 degrees north or so, the pre-PETM sediments that were deposited at this point in time are largely of a carbonate ramp variety. During the PETM, this shifts to a siliciclastic dominated system, which then recovers into the carbonate ramp facies that were being deposited prior to the PETM afterwards. And the authors of this study found that there was no change in the provenance of the siliciclastic material that was being deposited either before or during the PETM. And so therefore, they're arguing that the changes that are being observed are not due to a change in the tectonic regime that's happening at this time, but rather just an increased siliciclastic flux due to the intensified, more extreme precipitation resulting from the seasonal monsoon. In the southern Tethys in India, this is a more equatorial location, and we see a similar trend. You go from these carbonate type deposits that shifts into a conglomerate during the peak of the PETM. And again, this has been interpreted in the literature as this rapid deposition from this fluviodeltaic system, indicating an intensified hydrologic cycle occurring at this location at this point in time. So to understand what exactly is going on with the hydrology here and see how our models compare, I utilized the output from the CAM5 model. So purely atmospheric model run at a 1/4 degree spatial resolution. This was run for 20 years with a 6-hour time step. For the ocean boundary conditions, we use CESM 1.2, the fully coupled model, ocean atmosphere components, with a 2-degree resolution that was run for 1800 years with a 1-month time step. Between these two runs, I'm going to refer to them as LP or late Paleocene and the PETM. Methane was held constant. The Paleocene CO2 was at 680 parts per million. PETM was 1590. And due to increasing evidence of how orbit can actually was influencing climate during these Eocene hyperthermals, we also looked at the influence of orbit by utilizing both a circular orbit, which is to say that the insolation during Northern Hemisphere summer was the same as during Southern Hemisphere summer, as well as an elliptical orbit that maximized insolation over the Northern Hemisphere during the boreal summer. And I'm going to refer to this more elliptical orbit as the OrbMax run in all of my model output. So this is the first of the output I'm going to be showing you. So this is for the Tibetan location, so the north side of the Tethys. I'm going to be using the same color scheme here for all of the different model runs, wherein the black is going to be the late Paleocene, gray is going to be late Paleocene with that OrbMax configuration, blue is the PETM, so the high CO2, and red is the combining high CO2 and this more eccentric orbit. And there's a couple things that stand out here. One is when we hold the orbits completely circular, there's very little change in the strength of the monsoon when you apply the CO2 forcing within this model. So this is looking at the the average monthly rainfall that occurred. However, when we apply this enhanced eccentricity to the model that maximizes insolation during the Northern Hemisphere summer, in the late Paleocene, we have almost a quadrupling of the intensity of the monsoon, from about 100 millimeters in the month of August at its peak in the late Paleocene, going to close to 400 millimeters in August during the OrbMax configuration. However, when we apply the CO2 forcing to this same run, we see a reduction of about half of the total strength of the monsoonal signal, going from a peak of 400 millimeters a month to about 200. And this seems contradictory to the observations that seem to suggest enhanced seasonal precipitation during the PETM at this location. At the southern location, the model is more in line with our expectations. So again, the late Paleocene are in black and gray, and the PETM are in red and blue. And what we see here is a enhanced seasonal signal. So in the winter months, so January through March, there are drier conditions, and then in the summer months, there are wetter conditions during the PETM runs. So I looked not only at the seasonality of precipitation, but also the precipitation extremes. So in this plot, I'm showing exceedance frequency. So this is a log-log plot. The x-axis is showing the rate of precipitation predicted within the model. The y-axis is showing the frequency with which the model exceeded a given precipitation rate. And so basically the higher and further to the right that a line is, that's showing more extreme precipitation. And what you can see is that similar to the seasonality, the late Paleocene orb max configuration results in typically the most extreme precipitation, with a few outliers towards the end of the PETM orb max run. The PETM orb max results in the second most extreme precipitation. And then similar to the seasonality again, there's very little shift in the precipitation extremes between the late Paleocene run with the circular orbit and the PETM run with the circular orbit. Looking at the precipitation rate at the southern location, it's again more in line with what we would expect, where CO2 forcing results in an overall increase in the intensity of the extreme precipitation events. So to conclude, there are obviously different mechanisms that are driving the hydrologic change in the northern and southern Tethys, and there is an agreement between the interpretation of the sediment record and the model output in the southern Tethys. However, there is a conflict between the interpretation of the sediment record and the model output in the northern Tethys. So I don't entirely know why this is yet. Could it be these changes are actually tectonically driven? It would make it hard to explain the recovery, though. Could it be that there's some sort of problem with our model? Could it be due to our paleogeographic configuration that we're using? Could be different parameters I should use to look at this, or a different orbital configuration that I'm not getting. But if we trust the model, the influence of CO2 forcing on the South Asian monsoon appears to be highly dependent upon the orbital configuration. And so going further, I want to dive more into the dynamics behind this. And there should be further analysis of the sediment changes to try to disentangle tectonic and climatic effects. And there's a few other locations I'd like to look at, but since I'm out of time, I'm just going to wrap up and say thank you, and I'll take any questions.
Thank you, Will. I believe you have a question already in the chat. So I believe we should move on here.
Yeah, I can answer that in the chat.
Okay. And now we have Arnie Wingooth, professor at the University of Texas, Arlington, speaking on marine biological carbon pump during Eocene hyperthermals.
Thank you, Esther. I want to give you an update of long-term CSM 1.2 simulation. I acknowledge my co-authors and also the sponsors in support of the study. As we heard in the previous talk, the Paleocene-Eocene thermal maximum is of great interest because it's a suitable analog for future climate change, but it's also of interest for large changes in the carbon cycle, particularly the productivity and associated carbon flux as shown here on the right figure. The carbon flux is also important for marine species like foraminifera, and there's a notable extinction of foraminifera in the South Atlantic or Atlantic section during the PTM. So the carbon cycle is controlled by the particular organic carbon flux is controlled by photosynthesis, which itself is controlled by light, temperature, nutrient availability, and some mixing processes. One can now predict the productivity or hindcast the productivity of the past by using marine birite fluxes. And so these fluxes are somehow correlated to productivity, which is shown in the next slide on the left, where one has estimated the barite fluxes for the pre-PTM or the late Paleocene and the PTM. And that suggested that the barite fluxes increase, so the productivity. during the PTM. However, modeling results suggested the opposite, because one expect actually more stratification, less upwelling, and thus reduced upwelling. So we are using here a series of deep time modeling comparison project simulations, which I have described before, and then using also box modeling results to better estimate these productivity estimates and also carbon fluxes. So we have then set several simulations, and we have now been able to run with fully carbon cycle the late Paleocene simulation, which is equivalent to the 3 times CO2 simulation for 2,000 years with carbon cycle, and the 6 times CO2 simulation, which is the analog for the PTM simulation, is still running, is still in the machine, and we need to complete at least 700 more years. The associated climate changes in the simulation indicate substantial warming towards the PTM, and also a stronger rise in temperature over land compared to the ocean, warming of high latitudes, and reduction of the pole to equator temperature gradient. If we compare the PTM simulation, the 6 times CO2 simulation, with that of the proxies, we see reasonable agreement, but we still see some biases in the high latitudes, particularly in the Arctic region, and one can argue either it's a higher CO2 level, which would be a bit better fit, or on the other hand, maybe processes we are lacking, like cloud process discussed earlier. So the overturning circulation, here's shown the global MOG, is dominated from the southern hemisphere. So we have a southern hemisphere dominated MOG, which has been supported by a paper of Mikulevich and Meyer-Reimer in the 90s, suggesting if we're closing the Drake Passage and open the Central American Seaway, we are shifting the MOG to the southern hemisphere, to the southern dominant hemisphere. And then the MOG declines, the global MOG declines with increased CO2 radiative forcing, so consistent with multiple model studies. What's interesting is also we're noting at high CO2 levels starting at 6 and higher, we're starting also a shift in the circulation from a more polar ventilation and a thermal mode in the circulation to a more shallow deep water formation in the subtropics or the haline mode. So the productivity patterns are shown here quite similar to the CCSM3 simulation, with reduced upwelling, decreased overturning, and associated decline in the nutrient supply. And so thus we do have a reduced productivity. Shown also at the lower part here is the changes in upwelling, in particular, that is reduced at the equatorial region. There's also changes in the ecosystem dynamics, which will be explored as part of a PhD thesis. So we're somehow supporting the previous results. We are now able also to better predict the oxygen with these long-term simulations. And we noticed that the deep water formation takes place mostly in the Weddell Sea, and so we are ventilating the Atlantic from the Weddell Sea northwards, and we see then a decline in the oxygen at the bottom water. And if we increase the CO2 levels, so from the late Paleocene to the PTM, we would already have a lower dissolved oxygen in the bottom water because of the warming and the lower solubility. And then we have on top of that a decline in the deep water source and the Weddell Sea, and increased stratification, which leads a further decline in the oxygen, which does provide a stress in the foraminifera, for the foraminifera. So we looked also as a measure for the biological pump in the apparent oxygen utilization, which is determined by the oxygen saturation minus the simulated oxygen concentration. And for the late Paleocene simulation, we see a strong apparent oxygen utilization below the equatorial upwelling zone in the Atlantic. And that is due to the high amount of remobilization of particular organic carbon in the zone, which is also observed in the present day record. Now, of interest is now how does the apparent oxygen utilization changes if we are transitioning from the late Paleocene to the PTM. And what we notice is actually an increase in the oxygen utilization in the twilight zone. So Don Penman has looked in box models, the LOSCA models, and so the motivation were first looking in other times like the KPG boundary were noticed an enhanced remunerization. So if we have an increase in apparent oxygen utilization, that may be favorable for an enhanced remunerization. And so we carried out the simulation in a recently published paper of Liz Griffiths and company. So with this box model, we can actually predict an increase in the PCO2. So we can actually simulate positive feedbacks in the climate science due to the warming of the Paleocene Eocene summer maximum. Put up the conclusion, and I think my time is already quite progressed, and I'm happy to answer any questions in the chat.
Thank you, Arnie. We have, I think you're maybe have a minute for a question if there's one. Otherwise, we could take questions in the chat. And looking for a hand. Don't see one. Why don't we take some questions then in the chat, and we can start. I think we're now going to start our discussion. We have a brief discussion focused on some questions that we thought were kind of emerged from some of the talks today. Let me share my slides. Let's see. Okay, share. Here we are. Okay, I think everyone can probably see this, correct? I don't have to run the slideshow. Is that, can you see it, Arnie?
Yes, I can see it, yes.
Okay, yeah, because when I run the slideshow, it obliterates everything else on my screen, and I kind of want to see what's going on. So we thought we would have two short discussions with some focused questions for us to think about. The first is, what does paleoclimate modeling tell us about sensitivity of the Earth system to forcings? We saw a number of examples of this today in the talks that we just heard. Does anyone have a comment or contribution to this?
I think what we discussed, and I think what's important, what are the key factors contributing to the Earth system sensitivity?
Mm-hmm.
I think that discussed in several talks.
It seems like the cloud feedbacks are the biggest uncertainty, but also have the biggest impact to climate sensitivity. And so that's a real area that needs further research, but it's one that with better reconstructions that we have, our latest reconstructions, they really provide a much closer constraint on paleoclimate. That, for example, what John showed with the LGM reconstruction, now helping to constrain some of our choices for parameterizations in the model.
Esther, I have a question.
Oh, I do have, okay, sure, go. Go, Marcus.
We've been looking at the ventilation, and I think we're not the only ones, but there's a very poor Antarctic bottom water formation, which makes it difficult to, to get at LGM carbon budgets and other interesting questions. So that's, I think that's an order one problem. Is this being addressed, or are people addressing this right now?
In the ocean model, I think it's been an issue that they continually have been trying to address with the ocean mixing parameterizations. I think they're aware it's, yeah, one bias in the ocean model is that the ventilation in the North Pacific is very, very weak. And I think we'll see some examples of that in our next session.
Well, Antarctic bottom water as well. Right?
What?
Antarctic bottom water as well.
Yeah, and the mixing in the Southern Ocean as well. So the whole ventilation of the deep ocean is weak compared to what we think the ventilation should be in, say, the mid-Pacific, sort of the end point of circulation, where the oldest water is found it's very, very, very old in ideal age, and some of the other tracers like the carbon isotope, carbon-14 tracer. So yeah, I think it's something that Keith is no longer here, but the ocean modelers have been trying to work on over the successive versions of POP and now into MOM. So yeah, I think that is an issue that is forefront to be worked on, getting the deep ocean.
Well, it's not really mentioned in the publications either, right? You have to, I mean, it's not obvious to me that this is.
I think it's mentioned in Gökhan's paper. I'd have to check, but okay. I believe it's something that has been presented in some of the working group presentations. But yeah, it is an issue. I don't know who's next.
John, I think. John,
I think it's John, then Fran, then Andreas.
Andreas. Okay.
Okay. If it's okay, I'm going to ask a question. Ask Jen a question. It's related to this discussion. So my question is: so in your halving CO2 and doubling CO2 simulations, have you checked the SST pattern effect on the cloud feedback? So that has been discussed a lot in the community. And a related question is, what do you think about additional simulations with, say, SST plus 4K and SST minus 4K? Will that be helpful, or it just opens another box of questions? Thank you.
I think the first question is Jen K still here?
Yeah, I'm here. Those are great questions, Jenny. I'm happy to chat more offline as well. I think the pattern effect for a doubling and a halving, there's a lot of similarities. In particular, there's more warming in the tropical Western Pacific on this kind of fast time scales, and then on the slow time scales, like you get the kind of response in the Eastern tropical Pacific, but there are some nuances that are different in the patterns of the clouds under cooling than under warming. And I think it'd be fun to try to understand those and diagnose them more. And I guess just as long as I have the floor, I'll just briefly say that I think it's really fun to disable the cloud feedbacks. I mean, I think it's great that, we can make these minor tweaks to the model, like what Jang suggested, and it's kind of shocking that we can reduce the equilibrium climate sensitivity so much with so few little changes in the cloud parameterizations. And while I think that does lead to a more reasonable equilibrium climate sensitivity, I'm not really sure you're getting the right answer for the right reasons. And so there's a lot to think about there. And so I think simulations with the cloud feedbacks disabled might be helpful for kind of removing this layer of uncertainty that we know is really large. But I haven't done a lot in the paleoclimate world, so this is maybe coming out of left field a little bit.
Okay, Ran, I think you had a comment.
Thank you, Jen.
Sure. I would just like to echo some of what John and Jen said about cloud feedbacks, as well as looking into the equilibrium climate sensitivity a little bit more magnetically, especially there are a lot of effort in proxy community, which are very interested in using this almost like emergent constraint idea to constrain the equilibrium climate sensitivity from those SST proxies or even some of the terrestrial proxies. But a big question, a big problem, especially for well, even in quaternary, but especially for like Pliocene, Miocene, or Eocene, is there's no real serious thinking on the forcing. So a lot of people thought it's just CO2. So I'm just gonna take the CO2 as the forcing. And it's very much casually done a lot of times, like citing maybe one model simulation while the changes in boundary conditions cause maybe this much warming, and then that number has populated through literature. So I think there is a real need that we do a forcing intercomparison and constrain the forcings across model simulations and actually think about how much warming that is not due to CO2 across those paleoclimate simulations, and use that information to help the effort of using the proxy SSTs, for example, to constrain the equilibrium climate sensitivity. So I think that's kind of a, at least from what I see, that's kind of a gap in paleoclimate modeling effort in terms of helping tell the sensitivity of our system from the proxy records. Is we can provide better information on the forcing and the non-CO2 related responses. Yeah.
Thanks, Ren. Andreas?
Hi.
Hi.
I was wondering, after Marcus's talk, which was really interesting in looking at these CO2 responses, and suggests perhaps that iron fertilization played a role there for these millennial variations. And we have found also in a recent study that iron fertilization has probably been really important for glacial interglacial CO2 variability. So if that is the case, that means that an interactive dust model would be really good. And so I was just going to throw this out. So if there's any plans or so to include like an interactive dust model. I know that Natalie and others have done like LGM and snapshot simulations, but it would be nice to have it in a model so that you could do transient simulations.
Yeah. With it. Even for setting up paleo simulation, it would be really helpful if we have such a tool. I consent, yeah. And it's important, we see that since clouds are important, so is dust, yeah. It's not only for the BGC, but also for the clouds. Yeah.
I do know that the dust in CAM is a prognostic quantity, dust. So we do have, although it's kind of something that, like when we did our mid-Holocene and last interglacial CMIP6 runs, Natalie tuned the dust a little bit. So because we had to remove some vegetation feedbacks because our vegetation wasn't quite right for those time periods. So we kind of took that out, but it's, yeah, I mean, I think dust is important. I know for the LGM simulation, GOCON has questioned the role of dust in the LGM in our simulation. So.
Would it be difficult to have these tuning, what Natalie did as kind of, so you mentioned that depends on the vegetation, that we can somehow include that actively. So if you're changing the vegetation type, that we have also different dust fluxes, so that we don't need to compute that always offline.
Yeah, I'm not that knowledgeable about dust in CAM myself. I know that there's a dust emission factor that can be used to tune dust. I think it depends on the surface conditions, you know, the soils and the land surface. The TLAI, I think, is one of the factors it's dependent upon. Do you have any other thing to say? Jean is perhaps more knowledgeable about dust in CAM?
I guess this partly brings back to the discussion on vegetation, because the dust emission, of course, depends on the vegetation. In the current LGM setup, we are using the pre-industrial vegetation. And when we incorporate the phenology feedback, which means we have LAI changes, but no vegetation type change, we can see a big contribution on the LGM global cooling. So I think the point is that vegetation itself is already very complicated, and it impacts dust. So we need to think carefully about how to approach this overall problem regarding dust.
Right. Betty added in the chat that it's a good question for the land model working group. I think, you know, we could perhaps do more collaborations with the land model working group on some of these questions in the future. I mean, they provide us transient vegetation surface data sets, but I think we could do more joint projects closer with the land model working group members. So that might be a good place to. Betty has her hand raised.
So just to add, and maybe John can say something, the terrestrial sciences section of the land model working group are doing some perturbed parameter ensembles with CLM5, and they're quite interested in kind of perturbing or using scenarios with lower CO2. So not just looking at present day or high, but also low CO2. So hopefully there'll be some collaborations on that as they do these perturbed parameter ensembles.
Okay.
Esther?
Yeah.
While we are at the topic of plants, hi.
Yeah.
So permafrost would be something very exciting too, while we're at this interactive stuff. Is there a permafrost component planned? I think especially when you look for LGM transients, that would be a nice thing to have or to.
Can you say that again, Marcus? I know Peter has.
I think permafrost is something, is another thing. I mean, are there efforts underway to actually add an interactive permafrost model on top of the land model, which I think the land model actually is quite nice, but if you do go into LGM and want to look at the transients.
So that is a good lead in to Peter. Peter Lawrence here from TSS and the land model working group has raised his hand.
I just wanted to back up what Betty and you were saying, Esther, that the land model and the land model working group should be very closely related with what's going on in paleo. There's obviously a lot of overlap, and it's really important to test the model outside of, like, you know, our current observed climate forcing. This is one of the key areas. So yes, the perturbed ensemble is looking at like low CO2 levels. So can we run our model in a sort of in sort of paleo sort of situations, is it out of sample still working very well? The other component is, yes, we would be very excited about how do we better bring together vegetation dynamics, like what's happening with fates, being able to reproduce like paleo distributions of vegetation. So this is an exciting area that we'd like to be involved with. And obviously we've been involved in the last glacial maxima, not the last, sorry, the transient Holocene and the last millennia. So we could somehow create a project where we look at, well, how do we do dynamic vegetation going back in time in a systematic way that works well? And I thought there was a number of points that were brought up about how do you constrain the forcings that are put into paleo runs across models, and those sort of comparisons are really interesting. So yes, it's really important for us in the development of CLM or CTSM now to have these out of sample tests to understand if the model performs. It's one thing to say, okay, we get the current day right, or we get the historical period right. But if we don't get paleo situations right, that also tells us about what it looks like out of sample going into the future. You know, if our model has a certain CO2 response that it can't be supported by the paleo record, does that tell us something about how we project it forward under higher CO2 and higher climate scenarios? So yeah, I think this is really a great collaboration, and I'm excited and I'm glad that I'm here today. So thanks.
Great. Can you speak more directly about permafrost in CTSM? Are there
Oh, sure. So, I mean, one of the big things that we did in CLM5 was we now have 50-meter deep soils that go down to bedrock. And that was a big part of that was about developing frozen layers and being able to do permafrost representations. And Dave Lawrence has been one of the big drivers of this. So we do have these deep soils. One of the problems is obviously spinning up the model to get the deep peats that allow you to get the big carbon-rich soils in the Arctic. But we are looking at how do we resolve some of those issues. But this is definitely an active area for the Land Working Group and Dave Lawrence especially. But the other side of it is understanding what happens as we see permafrost thawing and then large carbon releases out of the peat that is currently frozen in the permafrost. But Dave Lawrence is, I guess, the big driver for that. I know that peripherally it's not my research, but I think it's definitely in a key area for the Land Model Working Group and also for CTSM. So
and the BGC group would be interested in changes in carbon fluxes from permafrost, and yeah.
Can I add a comment regarding the spin-up time of the deep soil? That is also an issue for ocean biogeochemistry, ice sheet coupling, and so on, all these processes that have long time scale. So for that reason, I would advocate for having a low resolution version of the atmospheric model that you can actually do these long time simulations easier.
Good point. Yeah.
So the one thing that Jean didn't comment on is the version he's using, FV2x1. He can now get 50 years per day on Cheyenne. So that's getting there. Of course, we'd like to have 100, 200. But yeah, if somebody wants to work with the T31x3, Marcus, that'd be great.
Well, I think it's a fantastic model. I mean, it has the same biases that the 1 degree model has, but it's much, much faster. And the spin-up time is actually doable. So yeah, you get 100 years per day on 5 nodes. I think it's 32 core nodes. So I think everybody can do this at home. So
yeah. All right. Where are we in time? I think we're running over our break a little bit, but we still have about 10 minutes to take a break. And I think we should, if there's no other comments, we could continue the chat conversation on the discussion. But also, I hope to see you all back after our break. We're starting back again at 10:30. And we have a great set of talks, a lot of work with modeling different time periods and comparing to the proxies. And then after the end of our second discussion, we will have a little lunch meetup for those who want to stick around and chat on some of these issues that we've been talking about, maybe build some collaborations And anyway, let's have a break. Thank you. Come on back afterwards. I'm going to Okay. I'm back. Let's see. Stop. Let's see. I am. Hello, everyone. I don't see my co-chair, Arnie. Let's see. Nope. Okay. Let's see. So we are now at 10:31. So I think we should just carry on here and get started with our second half of talks. Our first student, our first talk is Jiwoo Han from who's a graduate student at the University of UCLA. Sorry. She will be talking on diatom inferred water depth transfer function from a single lake in Northern California. And Jiwoo, do you want me to play your recording?
I think I can do that like live talk.
Okay, go ahead and share your screen.
Okay. Okay, hello, my name is Jiu Han. The title of today's presentation is Diatom Inferred Water Depth Transfer Function from a single lake in Northern California. Entering the 21st century, there have been many changes in weather and climate conditions around the world, and we are quite used to extreme weathers. In particular, California has experienced water-related disasters such as severe drought and fires frequently in the 21st century. And its scale and frequency have become larger, more destructive, and prolonged. To reduce damages and costs, it is important to predict and prepare for the climate changes. To this end, climate modeling can be a useful tool. Climate modeling can predict future climate change, but it can also simulate the climate of the past. By modeling the past climate, we will be able to get a hint of what will happen in the future. Therefore, to simulate the past hydroclimate changes in California is my research goal. To do so, diatoms, which is a phytoplankton, are chosen as a proxy indicator in this study to investigate lake depth changes. The reasons why diatoms are a good indicator are that they respond to lacustrine environmental changes sensitively, they are common and primary producers in lake environment, and they are well preserved in lake sediments due to their silica shells. Using diatom records, I will especially establish a water depth transfer function that can estimate paleohydroclimate changes quantitatively. And the transfer function will be helpful to paleolimnological studies and predicting and preparing for future hydroclimate changes eventually. So the research site of this study is Kelly Lake, which is in Klamath Mountains, Northern California. The location is about 10 kilometers away of linear distance from the border between California and Oregon. The lake is around at 1,346 meters height in California coast ranges. Klamath Mountains have low precipitation during summer and high rainfalls during winters with moderate seasonality in temperature. Based on the backgrounds, two research questions can be asked in this research. One, is there a correlation between lake depth and diatom assemblage in Kelly Lake? Two, is a single lake with a small size and mid-water depth applicable to establish a diatom inferred water depth transfer function? To accomplish this research, the surface sediment samples were obtained from Kelly Lake. The McDonald lab members of UCLA and Kirby lab members of CSU Fullerton went to the lake in July 2019. Overall, 40 samples for the top 5 centimeters of lake sediments were taken using the mini glue coral. While taking the samples, the observed depth and the Secchi depth were measured too. The lake was deep enough for this study, which was 5.2 meters deep for the deepest portion. The Secchi depth were measured by a Secchi disk. It is to see how deep sunlight can penetrate in the lake. Because diatoms are phytoplankton and do the photosynthesis, knowing the depth of photic zone is also important to understand the ecology of the diatoms. Also, the water chemistry was measured to understand the lacustrine environment better. From the measurement, we knew that Kelly Lake was a freshwater according to its low salinity and is oligo to mesotrophic. Also, the lake seemed pretty warm during the summer. The map below shows points where the samples were taken. The red lines are the 3 transects that we made. Except the 6 samples that were taken at the margin or near the lake, we collected all the samples within the lake while trying to hold various depths at a regular interval along the transects. Every time we collected the surface sediment samples, observed depth and the Secchi depth were also recorded as well as the coordinates for each point. After preparing diatom microfossils with some chemicals, diatoms were counted under the oil immersion light microscope with a magnifying power of 1000. At least 400 valves were counted per slide at species level. These are the diatoms from Kelly Lake. Most species are benthic, which lives on substrates such as plants or sediments, and there are also a few of planktonics. The diatom identification followed the taxonomy after Kramer and Lange-Berthelot in general, but some species were classified according to the updated information. There are about 150 different species identified from the site, and the dominant species which exist more than 1 or 5% at least one sample is chosen for the further statistical analysis. This diatom diagram is drawn with the 21 dominant species which exist more than 5% at least one sample. Using a depth-constrained cluster analysis, the diagram is divided based on the water depth zones. The 3 depth zones are named as shallow, mid-depth, and deep zones. This zonation is assessed by one-way analysis of similarity to make sure if the zonation was correct. Due to the time constraint, I'm not going over the details of the diagram, but you can read each species fluctuations in percentage along the depth in Kelly Lake. According to the graph, it seems there is a good correlation between diatom flora and water depth in the lake. For the remained statistical analysis, the diatom species which has more than 1% abundance at least one sample was analyzed. First of all, one-way analysis of similarity was conducted to test how similar the diatom community is between the depth zones. And it showed that there exists a difference between the depth zones. In the result of the analysis, it offers p-values and r-values. P-value indicates how significant the differences between the groups, and the r-values indicates the strength of the factors on the samples. And according to the values, we were able to read the results as there are different diatom communities between the 3 depth zones, and lake water depth is influential factor to the diatom composition. With this diatom dataset, we established 2 transfer functions by using 2 methods, such as weighted average pressure least squares, WAPLS, and modern analog technique, MAT. After establishing transfer functions, you can compare them by reading R-square and RMSEP values. R-square is the coefficient determination, and RMSEP shows the error between the observed and the expected values. So the lower the value, the more significant it is. Overall, both WAPLS and MAT transfer models show high R-square values and low RMSEP. Especially, MAT performs better than WAPLS with lower RMSEP. However, the reconstructed depth in the mid-depth show quite over-representation trend in MAT, and WAPLS showed better performance for the mid-depth.
About 2 minutes.
We also demonstrated residual scatter plots for the assessment of the transfer functions, and it showed that the residuals in both models do not have tendency. To sum up, there was a clear correlation between lake depth and diatom assemblage in Kelly Lake. The performance for both transfer functions was good, but MAT transfer model performed better than WAPLS. And the diatom inferred lake depth inference model from the coast ranges of California was successfully established and showed the relationship between diatoms and water depth quantitatively. There are some future works of this study by adding more modern diatom data to make it more robust and applying the downcore diatom data to reconstruct past lake water depth changes quantitatively, which is in progress. Thank you for listening. I appreciate any questions and comments. Thank you.
Thank you, Jihu. Let's see. Don't know if we have really enough time to take a live question, so maybe we'll take some in the chat.
Okay.
Yeah. I would say your research site looked awesome to go and gather samples at.
Yeah.
All right, our next speaker is Chi-Jung Sun from the University of Texas at Austin. I believe Chi-Jung is a graduate student currently. You're muted, by the way, and you can start sharing.
Okay.
Yeah.
Right. Awesome. Thanks. Thanks for the introduction, and hello everyone. Thanks for having me. Today I will show you our study about past changes in the Great Plains storm intensity and as well as its relationship to land surface temperatures. So the Great Plains of the United States is visited by frequent large convective storms called mesoscale convective systems during the warm season. And these storms, they are often accompanied with damaging hails, winds, and floods, and they can be quite destructive. And this data show that in 2020 alone, there were more than 10 of these storms that can be characterized as billion-dollar weather and climate disasters. And over the last 3 decades or so, it has been observed that MCS rainfall is increasing at a rate of 25 to 28% per decade. This certainly raises concerns about how and why these changes occur and how would these systems change in the future. On one hand, the increasing temperature over the last few decades could partially explain the enhanced storm activity due to the thermodynamic effect. And on the other hand, land surface warming could also affect the dynamics of these systems and thus drive changes in MCS rainfall. So here is an illustration of the dynamics of MCS. During the warm season, southerly winds called the Great Plains low-level jet. It develops and brings moisture from the Gulf of Mexico into the central US. And when the low-level jet meets with the upper-level jet stream and interacts with its embedded frontal systems, mesoscale convective systems would occur, and they could last for from several hours to days. Because the low-level jet is a geostrophic wind that is strongly affected by the pressure gradient between the land and the ocean, it has been hypothesized that the increasing land-sea temperature contrast over the past decades could drive an intensification of the low-level jet, which would fuel the MCSs with increased moisture supply, and thus can be responsible for the observed changes in MCS rainfall. However, how robust is this mechanism remains to be tested. And instrumental records are usually not long enough, and unfortunately, paleoclimate records from this region are extremely scarce. Here, we report our new paleoclimate reconstruction using sediments from Horse Cave. Horse Cave is located in central Texas. MCS accounts for the majority of its warm season rainfall in this region, and spring is the wettest season of the year because this is when MCS occurs most frequently. And the pictures on the lower left shows what the cave and its sediments look like. These sediments are transported to the cave when rainfall occurs. And here we use a multi-proxy approach. First, we use the hydrogen isotopic composition of sedimentary leaf wax to reconstruct MCS activity. This interpretation is based on our monitoring of environmental controls on the stable isotopic composition of rainwater. On the right-hand side, we show that the daily rainwater isotopic composition are positively correlated with the outgoing long-wave radiation, suggesting that the isotope values are lower when there is a bigger storm. We then use the carbon isotopic composition of bulk organic matter to reconstruct changes in vegetation. In this region, the vegetation landscape is strongly controlled by precipitation and moisture availability. And finally, we use the percent titanium as a proxy for erosional runoff, which indicates extreme rainfall events. And here is our data. The leaf wax time series is shown in blue, and superimposed on it is the percent titanium record in red, and at the bottom is our carbon isotopes in green. Our multi-proxy records from Hawes Cave show remarkably coherent changes over the past 20,000 years. And notably, during the late glacial period, our data show that the MCS activity was weak. The landscape was dominated by C4 grasses, and near 14.5 thousand years ago, and there was a rapid increase in MCS activity and an expansion of trees. And also note that this event spans across both the Bowling, Alrod, and Younger Dryas. And during the Holocene, there is a gradual decrease in MCS from the early to mid-Holocene, and it's followed by a gradual return towards more MCS activity towards the present. The consistency between these independent proxies suggests that there are strong connections between changes in large-scale convection, extreme precipitation, and ecology in the central US. And in order to understand what drove the evolution of MCS and hydroclimate change, we utilized the TRACE-21K simulations produced at NCAR. We focus on the spring season because spring is the season when the large-scale conditions are most favorable for MCS genesis. And since spring is also the wettest season, our proxy records are likely dominated by the springtime signals. We also define a low-level jet index to characterize the evolution of the low-level jet. It is selected based on the region of the strongest southerly flow over the region. The simulated low-level jet shown at the bottom of this figure is consistent with our proxy records. The low-level jet shows a sudden jump near 14,000 years ago and a gradual weakening from early to mid-Holocene, followed by a gradual return towards the present. And this suggests that changes in the intensity of the low-level jet exerts the dominant control on past variations in storm activity. And next, we will use TRACE to understand what drove those changes in both low-level jet and storm activity during the deglaciation and Holocene, respectively. First, let's look at the deglacial climate change. As you can see on the left-hand side, in TRACE, intensity of the low-level jet occurs right at the same time as the accelerated retreat of the North American ice sheet. The sudden retreat of the ice sheet causes the land to warm dramatically as a result of changing albedo. And this warming drives a low pressure anomaly over the land and a high pressure anomaly over the ocean. Together, the zonal pressure gradient would be steepened, which would ultimately intensify the geostrophic low-level jet and intensify the mesoscale convective systems. And then during the Holocene, the gradual nature of the MCS evolution suggests that it is associated with the orbital insolation changes. Our record shows that it is in phase with the springtime insolation change rather than summertime changes. This makes sense because of the dominant role of springtime MCS activity in this region. And now let's look at the dynamics of the of MCS on the right-hand side. This map is showing the climate anomalies of pre-industrial minus the mid-Holocene. As we can see here, the land surface warms much faster than the ocean. Okay, thanks. Due to the lower thermal capacity. And once again, the low pressure system over the Rockies intensifies due to warming, and the North Atlantic subtropical high intensifies as well due to the larger temperature contrast. And these result in a steeper zonal pressure gradient between the land and ocean, which makes the low-level jet stronger today than the mid-Holocene, which also explains the increasing storm activity from the mid-Holocene to the present. And in conclusion, we show that past climate changes over the central US reveal high sensitivity of hydroclimate and extreme weather to springtime land surface warming. Changes in the springtime low-level jet intensity were the main driver of past storm variability over the last 21,000 years. With the globe continues to warm, we anticipate that there would be increasing risks of extreme weather over the central US in the future. And that's all. Thank you.
Thank you, Chi-Chung. Very interesting. Let's see, I think we should move on and ask our questions and have discussions in the chat. Our next speaker is Lingwei Li, a graduate student at Ohio State University.
Great. Hi there. Thanks for the introduction and oops.
Oh, yes.
Let me present.
Did not give your title.
Yep, I'm glad to have this opportunity to present my this work to testing method to reconstruct glacial Antarctic superpollutant carbon transport in an isotope-enabled climate model. We believe a robust method to reconstruct the ACC Biogeochemistry transport is helpful to assess how the Southern Ocean responded to the paleoclimate conditions. Great. So physically, the ACC is dominated by its baroclinic transport as ACC is in the thermal wind balance. This means that ideally, the ACC baroclinic transport can be estimated from 2 or even 1 vertical density profiles on ocean margins across the ACC, which is verified at the Australia section. This is because the horizontal density gradient can be approximated from 2 vertical density profiles, and then the single vertical density gradient reflects the horizontal density gradient because of oceanic subduction process. So the density around the southern side is quite uniform and can be approximated from the density at the bottom depths on the northern side. So, however, in reality, we don't have observations for even 1 single density profile. Instead, we could have estimations for 3 endmembers, water masses, and 1 vertical profile of the calcite data 18. So the calcite data 18 cannot be directly used in the Southern Ocean under the cold climate because the relationship between the seawater data 18 and the salinity would change by the sea ice formation. So the question here is how to reconstruct the density profile at the LGM based on these 3 endmembers and 1 single calcite data 18 profile. So Lynch Stiglitz 2016 proposed method that combines endmember water masses and calcite profile, calcite data 18 profile, because most of the column north of the ACC can be well approximated as a linear mixture of surface water and intermediate water and bottom water and intermediate water in the modern temperature, salinity, and seawater data 18 relationship. So therefore, we access the method in Australia section in an isotope-enabled climate model, ICESM. In the meantime, we also hope to find some possible improvements in the reconstruction method. We start the most ideal case. Here, we assume that we have temperature salinity, and density observations for these three end members and the vertical calcite data weighting profile at Australia section. The density profile actually can be well reconstructed reasonably very well. So here it shows the model and the reconstructed temperature, salinity, and the density profiles and the bottom. So the dashed lines here are from the reconstruction and the solid lines are from the model. The temperature can be reconstructed very well, but we can see a large discrepancy between the model and the reconstructed salinity profile between the intermediate water and the bottom water, mainly because of the reconstruction methodology. Therefore, the density gradient can be underestimated. Fortunately, the result can be greatly improved if we have one additional pore fluid observation at 1 kilometer. Yeah, the pink marker here refers to this additional pore fluid observation. So as shown in this figure, the reconstructed salinity profile are much closer to the model profiles below the intermediate water depths, especially at the LGM. So consequently, the reconstructed density profile and transport are relatively closer to the model values in this case. So here is it's just that adding more direct information about temperature and salinity from pore fluid could reconstruct the LGM ACC transport very well. Then the observational condition is more constrained. Now we only have a density observation for bottom water, and the salinity of surface water and intermediate water have to be reconstructed independently. So because the relationship between the seawater data weighting and salinity in the surface and intermediate waters is almost linear, and this linear relationship is verified to be controlled by similar linear process as the LGM as today in the ICESM. So once we get numbers of seawater data weighting for surface and intermediate waters, we get estimates of salinity. Unfortunately, we cannot pin down the relationship, this relationship at the Australia section. We verify that the relationship between the surface and intermediate waters can be reproduced in the South India Ocean as a result of mixing between the subtropical jar waters and high latitude freshwater end members. So the results are quite interesting. When we look at the reconstructed salinity profiles, the salinity can be reconstructed relatively okay at the pre-industrial period, but changes dramatically at the LGM as the reconstructed salinities are quite overestimated. So therefore, the density gradient is hugely underestimated. Additionally, since paleo density profiles and paleo water masses values are reconstructed from proxy data instead of simply extracting them from the model, they are subjected to a number of uncertainties. Therefore, we also perform Monte Carlo estimation in this case to assess sensitivity of the reconstructed paleo salinities and ACC transport. So the rest, the test shows that this case would yield a very large error of the transport calculation, and the uncertainties in estimating surface and intermediate water temperature and salinity account for much of the total error on the transport calculation. So, but overall, we believe that a modest direct measurements of pore fluid of temperature and salinity.
2 minutes.
Yep. Interpret based on the calcite data weighting profile is a viable approach. So that's all about my this work, and I welcome any comments and questions.
Oh, I think do you have another slide? No?
No.
Okay. Do we have any questions? We have about a minute or so to take. Otherwise, we could, don't see hands. Or do I? No. I guess we'll take questions and comments in the chat then. Thank you, Ling.
Thank you.
Thank you, Ling Wei. Let's move on to Clay Tabor's talk. Clay is an assistant professor at the University of Connecticut. He'll be speaking on storminess and isotopic changes in the Western United States at the last glacial maximum.
All right, great. So thanks for having me. Yeah, so I just wanted to talk on a little update we've made on looking at Western US isotopic change at the last glacial maximum. And this is work I've done in collaboration with quite a few people shown here and others that are not on here as well. Oops. All right, so why are we interested in the Western US at the last glacial maximum? Well, it's kind of a unique hydroclimate response at the LGM. And so here in this first panel here, we have changes in overall wetter and drier conditions, with drier conditions shown in red and wetter conditions shown in blue for the last glacial maximum. What we can see is this kind of dipole pattern where we have wetter conditions in the northwest and drier conditions in the northwest and wetter conditions in the southwest. And on top of that, we have a lot of isotopic records, particularly from cave speleothem records, that are showing a lot of variability and change throughout the deglaciation. But what exactly these delta 18O signals from these cave records are telling us can be kind of difficult to deconvolve. So in order to better understand the Western US hydroclimate response at the last glacial maximum, we used the community Earth system model. And in this version, we have water isotope log tracers in a version of the model known as CESM 1.3. And the model generally does a fairly good job at simulating the present day isotopic distribution of precipitation. If you want more information about the strengths and weaknesses of the model, check out some of these references shown here. For the talk today, I'll just be looking at two time periods. One is the last glacial maximum and one is the pre-industrial. And we're using 1 degree configuration of the model. So we initialize these runs from iTrace simulations, and then we increase the atmosphere and land resolution to 1 degree in order to better simulate the topography of the Western US. And we also added high frequency outputs to look at storm activity and water tagging to look at where moisture sources originated. And we'll be comparing these with speleothem delta 18O records from the CESL 2 database. So all these plots I'll be showing for the next few slides are anomalies between the LGM minus the pre-industrial. And here I'm just looking at the isotopic response on the left panel here. This dashed area is where we have the Western US as we've defined it. And what you can see is that at the LGM, there's a significant depletion in the delta 18O precipitation throughout most of the Western US. And we also see in the right panel here, the precipitation response where we get this drying in the northwest and this increased moisture in the southwest, generally speaking. All right, so delta 18O precipitation is a weighted quantity. So it's most influenced by when you have the most precipitation. And in the Western US, that tends to be in the winter months. So here I'm just showing the same plots, but for winter delta 18O of precipitation change on the left and winter precipitation change on the right. And they generally reflect the annual mean signal, primarily due to the fact that they're largely driving the annual mean response. And so for the next few slides, I'll be looking primarily at the winter responses. And in this case, I've defined winter as November through March. All right, so we did some tagging experiments looking at the different sources of moisture to the Western US at the LGM. And what we found is that this region outlined here, which I'm calling the Central East North Pacific, is really the primary driver of the isotopic signal and the isotopic change at the LGM. And so this is the delta 18O precipitation change in the winter months. from this particular region, so moisture coming from this region in the top left panel. And then the delta 18O of the water vapor associated with that precipitation. So what you can see is there's a clear correlation between the isotopic response of the precipitation and the isotopic response of the water vapor. We also see that the LGM in these bottom two panels, that the total amount of water vapor coming from the Central East North Pacific region and the total amount of precipitation coming from the Central East North Pacific region has increased relatively. So it's contributing more to the overall signal at the LGM. So what's really driving this increase in moisture from this Central East North Pacific region? Well, we did some experiments using the Tempest Extremes code to look at the change in extratropical cyclones and change in atmospheric rivers, shown on the left and right in the top panels respectively. What we can see is that at the LGM, we get an increase in extratropical cyclones and there's somewhat of a southward shift possibly in extratropical cyclones as well at the LGM, but we don't see a significant increase in atmospheric river activity. And so part of this could be related to how the atmospheric rivers are identified. And because we have such cooler temperatures, we have a lot less water vapor in the atmosphere overall. But we see actual decrease in atmospheric rivers in the northern part of the study region, and then a kind of a maintenance atmospheric river activity a little bit further south. And so even though we're not necessarily getting an increase in atmospheric river activity, we're getting more or less maintenance of integrated vapor transport, as shown here in the bottom right, in the southwest region. And that's somewhat substantial because we have significantly less water vapor in the atmosphere overall. So there's actually a significant increase in the low-level jet shown in the bottom right here that helps to maintain that vapor transport, despite this reduction in total water vapor of the column at the LGM. So even though we have this maintenance of the integrated vapor transport, this doesn't really explain why we have increased precipitation in the southwest with the LGM. And so what we find when looking at vertical cross sections is that a lot of the signal is really due to increased precipitation efficiency or increased rainout of precipitation relative to total precipitable water in the atmosphere. And so one of these figures, just to kind of highlight this, is this different and constant density lines. The blue is the LGM and the red is the pre-industrial for a cross section around 40 degrees north across the western US. And what we see is much steeper lines of constant density at the LGM. And so what's going on is you have this increased isentropic upglide of these density gradients, leading to more rainout and more precipitation efficiency, as shown in this bottom panel here. And what that does is that leads to increased depletion as the water vapor moves inland and helps to produce that depletion signal overall. And finally, this depletion signal is also partly due to changes in seasonality of the precipitation. So winter precipitation overall is more depleted than summer precipitation for both the pre-industrial and the LGM, as just shown in this example on the left here. And we also in the LGM get more of our total annual precipitation from the winter months. And so that more depleted signal gets translated and into the annual signal because you have more of this winter precipitation at the LGM, as shown in the percent differences in precip on the right. All right, so we can compare with the speleothem records, and my collaborators have collected several different speleothem records from our study region. And these records are transient records through most of the deglaciation, but unfortunately, none of them really extend all the way, or few of them extend to present day. So we can't really work with anomaly space here, comparing pre-industrial to LGM. We're really just comparing the absolute values of the LGM simulations with the speleothem LGM measurements. And so what we did here, and this was really the work of my collaborators here, is use the ICESM outputs of things like delta 18O, the precipitation amount, temperature, and evaporation, and put those values into these forward proxy models, cave calc and karst dilution. And so then we just compared the speleothem measured delta 18O at the LGM with our model simulated LGM values. And so the actual measurements are in black, and then our comparisons for these different cave sites with our different model, forward proxy model outputs are in these different colors here. What we find is that overall, we're doing a fairly good job at capturing this isotopic signal at the LGM. And we do an even better job for some of these caves where we have monitoring ongoing, where we can refine some of the different knobs in the forward proxy modeling, as shown in this bottom plot here. We don't get great comparison in cave without a name, but that's a little bit outside of the study area. And there's a bias in the pre-industrial configuration of ICESM for this as well. So we think this is kind of a systematic model bias here. All right, so just to summarize, the ICESM simulates depletion and the delta 18O precipitation in the Western US at the LGM. And this doesn't completely align with the precipitation itself. But the delta 18O precipitation response is largely due to increased rainout as moisture moves inland and increased winter relative to summer precipitation compared to pre-industrial. And the model overall is doing a fairly good job at comparing with the speleothem and delta 18O measurements. So I think I'm probably out of time, but what we're doing from here on out is trying to use higher resolution simulations in order to better understand the small scale variability and trying to resolve some of these topographic features which might lead to more or less change at the LG. And with that, I'd be happy to take any questions.
Thank you, Clay. Nice talk. I think we should move on and take Clay's questions or any discussions in the chat. Our next speaker is Changfei He, a research assistant at Ohio State University. And he will be speaking on abrupt Heinrich stadial 1 cooling missing in Greenland oxygen isotopes.
Thank you, Esther. So good morning, everybody. So today my talk is about the glacial climate change and the associated water isotope over Greenland. So I mostly focus on the onset of Heinrich event because it seems invisible from the Greenland ice core record. So as you may know, the Heinrich 1 event and the Younger Dry event are caused by the slowdown of the AMOC during the last glaciation. And these two events are well captured by a number of proxies, like the seas of temperature in the North Atlantic, as well as the spectrum data 18 in the Asian monsoon regions. However, local to the North Atlantic, the Greenland data 18 seems largely unchanged at the onset of HS1. So even though it shows a clear abrupt change at the onset of Younger Drought. So this is actually very weird. How could it be possible that in two similar events, one had this clear abrupt change, but the other one just doesn't? So our question here is the onset of HS1 really muted in the Greenland ice core record? So to understand this part, we did the ITRI simulation. The ITRI simulation is isotope enabled transit climate simulation for the last deglaciation. So forcings of ITRIs is quite similar to the previous TRIS 20KE simulation. But in ITRIS, we have 4 runs with factorized forcings. So first run is deglacial retreating ice sheet. And on top of this, we add orbital forcing, then the greenhouse gas forcing, and finally, the meltwater forcing. All these 4 runs were integrated for 9,000 years, from 20K to 11K that covers the whole deglacial period. And the most important thing here is that we have stable water isotope incorporated in the model. So we are able to compare the model data routine with the observation directly. Now let's move back to the Greenland. Let's see how the climate change in ITRIS performs with the observation. So on left axis, it is model variable, and on the right, it is corresponding observation. In each panel, we are doing an apple-to-apple comparison. First, we see the data 18 is actually well reproduced. As we see, the purple and black curves are quite close. We have a muted HS1 onset, and we have abrupt change at the beginning of the Younger Drought. And for the surface temperature, it is also well reproduced. We see the surface temperature is quite consistent with the reconstructed temperatures, but except at the onset of HS1. In the model, we see the red curve, it has a clear abrupt cooling, but this cooling is not seen in the observations. So even though this cooling is not seen in the observations, this cooling in the model is actually quite consistent with other proxies, like the sea surface temperature in the North Atlantic and the spectrum data 18 in Hulu Cave in East Asia. They are all consistent with the slowdown of the AMOC. So here, the ITRIS suggests that the data 18 is muted, but the temperature is not. Then why? Because model is wrong or something missing in observation. Previous studies suggest that the change of the ice core data routine is composed by the change of the precipitation seasonality as well as the isotopic composition. So an increase in precipitation seasonality would enrich the ice core data routine because, for example, an increase in the summer precipitation would lead to the ice core data routine accumulates more the heavy summer isotope. And for this isotopic composition, it is affected by several factors like the surface temperature, the source of the moisture, as well as the strength of the inversion layer. So based on this idea, we analyzed these two effects over Greenland during the last glaciation. What I show here, the red curve is the isotopic composition effect, and the blue and orange curve are the precipitation seasonality effect. We see they're actually canceling each other during the most of the time in the last glaciation, in particular in HS1 and Younger Dryall. And the net effect is the black curve. It is the change of the ice core data routine. And then why these two effects are canceling each other in these two periods? So for this isotopic composition effect, I further analyze the seasonal evolution of the surface temperature. What we see here, the red curve is the summer surface temperature. During the last glaciation, it is almost like a constant, and so does the data routine in precipitation. But for winter temperature, it reduces a lot in HS1 and Younger Dryall. And due to temperature effect, the data routine in precipitation also depletes. So a decrease in winter precipitation leads to this depletion in the isotopic composition. And for the precipitation seasonality effect, we also check the precipitation evolution. We see quite similar to the winter surface temperature. The winter precipitation also reduces a lot in HS1 and Younger Dryall, even though the summer precipitation increases in a linear way. So as a result, an abrupt change of the winter precipitation leads to an enhanced precipitation seasonality. Therefore, it leads to enrichment in the ice core data routine. So here we find that actually it is winter climate that determines these two effects. A decrease in winter temperature leads to a depletion in the isotopic composition, and a decrease in winter precipitation leads to this enhanced precipitation seasonality effect. So the question is, what controls this winter climate change in the Greenland? Actually, we find it is because the sea ice, wintertime sea ice in the North Atlantic. What I show here is the leading mode of the maximum covariance analysis between the wintertime sea ice and the climate change in the North Atlantic. The leading mode accounts for more than 99% of the total variance. So they suggest that the winter sea ice and the climate change in the North Atlantic and Greenland are highly coherent. And this coherence is because the sea ice controls the water source and energy source for the Greenland. First, for the water source, for example, an expansion of the sea ice from LGM to HS1 would shut off the evaporation in the North Atlantic. So the precipitation over Greenland reduces in winter. Therefore, it leads to an enhanced precipitation seasonality effect. Well, for this energy source, so an expansion of the sea ice would also shut off the heat flux from the ocean to the atmosphere. So there is a widespread cooling in the North Atlantic during Heinrich-Run events. Due to temperature effect, the data routine water vapor also depletes, and therefore the data routine precipitation over Greenland also depletes. So this is linked to the depletion in the isotopic composition effect. Well, at the onset, from LGM to HS1, the sea ice expansion is much smaller compared to from boiling area to Younger Dryall, because the LGM is much colder than the boiling area. So the sea ice energy is much southward. Therefore, a smaller sea ice expansion leads to these two effects actually largely cancels each other, lead to a largely muted data routine response at the onset of HS1. But later, at the onset of Younger Dryall, that it is all dominated by this isotopic depletion. Therefore, we see a clear abrupt change at the onset of the Younger Dryall. So further, our study suggests that there is abrupt cooling at the onset of HS1 because of expansion of the sea ice. Therefore, based on this analysis, we suggest that if we rely on the data routine to infer the cooling in past Heinrich events, so these coolings are likely to be underestimated. So to summarize here, the take-home message is that the data routine and the climate change in Greenland during the last glaciation is controlled by the wintertime sea ice in the North Atlantic. Yeah, thank you. I appreciate your time. So if you have any questions, please feel free to
Can you repeat your last statement? I think I might have kind of.
Okay, so yeah, if you have any questions, please ask.
No, I mean your take-home message.
A take-home message is that data wetting and climate change in the Greenland during last glaciation is controlled by the wintertime sea ice in the North Atlantic.
Thank you, Changfei. Nice talk. And we have a minute maybe for a question. If anyone has a question for Changfei. So sometimes people are catching up in the chat with previous talks. It's kind of hard to juggle all of these windows and try to listen to a talk and also comment on previous talks. So bear with everyone.
Shall we move on?
Yeah, let's move on. Next, we have Hannah Zanowski, who's a postdoc at the University of Colorado here in Boulder. She will be speaking on Pacific Ocean 14C, radiocarbon evolution during the deglaciation in the sea iTrace simulation.
Awesome. Thank you, Esther. I should also let everyone know that this fall I will be starting as an assistant professor at the University of Wisconsin-Madison, so pretty big deal. So just to set the stage for everyone here, the glacial circulation of the Pacific Ocean was actually a lot different at the LGM than it was today. And you can kind of see this from this sort of schematic from Matsumoto et al. 2002 on the right in this picture. Which basically shows sort of the deep inflow of the bottom waters, outflow of North Pacific deep water, and also some inflow of North Pacific intermediate water and such. And so the major differences between the LGM and present day Pacific circulation are really just the fact that this inflow of the Pacific deep water was much deeper than it was in present day, and also increased North Pacific intermediate water. And so as a result of that, that then of course impacts carbon-14 and the circulation and the ages in this in these two time periods. And you can kind of see that from these two sections from Ray et al. 2020 of LGM and modern day carbon-14 age, where you see really, really old carbon-14 ages in the deep Pacific and relatively younger ages in the upper ocean. And so one of the questions that we have, though, is how do we go from this LGM circulation to the circulation in the present day? And so to be able to answer that, we're going to use the simulation called sea iTrace. This is a 3-degree ocean-only version of the CESM 1.1. It was run from 22,000 years ago to present day. It's forced with a bunch of different fluxes from the Trace 21 simulation, and it also has isotope tracers enabled in it. So we can kind of get at these sort of circulation changes, particularly by looking at carbon-14, and that's what I'm going to look at in the Pacific. So this figure on the right is just a sort of summary, if you will, of the sort of major forcings. We got the prescribed atmospheric carbon-14 in the black line, the increasing atmospheric CO2, which is also prescribed in this model, as well as some of the major sort of circulation metrics and the freshwater horsing in the northern and the southern hemisphere. So this model is capable of sort of modeling the periods of abrupt change throughout this time period. So diving right into the carbon-14 though. So what I have here are zonal mean sections of carbon-14 at various time periods throughout this model simulation. The top is the actual carbon-14 values, the bottom is the carbon-14 age. And so largely kind of what you're seeing from this is, even though we've kind of subtracted the atmosphere out, there's this large scale sort of decline in the carbon-14 values in the ocean, and sort of this, basically overall making the waters younger over time as well. Now, if you kind of compare this to present day though, this model is still fairly biased. So we take the present day values of the sea iTrace simulation, we subtract the GLODAT values from that, and this kind of gives you a sense of what the biases are in this model. And so that does then, of course, lead to relatively older ages within the model. And that, again, is tied to the fact that the circulation in general is far too sluggish within here. So nevertheless, though, we can go ahead and then compare our isotope, the isotopes within the model, though, to core records around the Pacific Ocean. So that's what I'm doing here. We're looking at carbon-14 ages. These are benthic minus planktonic ages for these cores, which are in purple. The model is in black. And then the gray line over time is basically a sort of a corrected version of this model or an adjusted version where basically I'm just shifting the entire record up or down based on the bias relative to the modern day bias relative to GLODAP. And that's just to kind of get a sense of how much this bias can actually sort of affect the ages that we get. So again, there are a lot of differences compared to these cores, but at the same time, if you kind of look at these things closely, you do see that this model is actually capable of seeing or at least simulating some of the carbon-14 age variations that we do see in these core records. And so I think that is actually really interesting. And so these are sort of point-wise comparisons between like one grid cell in the model and then the cores. So to understand something about carbon-14 circulation, and in particular circulation within the Pacific Ocean, then what I'm doing here now is I'm just showing you averages in sort of larger boxes within those regions, in the same regions that contain those cores. And so this is now bottom, again, benthic minus planktonic, if you will, carbon-14 over time within these same regions and in the blue. And then what I have are two other ocean tracers that we use in this model, ideal age, which basically is set to 0 at the surface and it just ages in the interior. That's a measure of the circulation age. And then ventilation age, which is set to 0 at the surface, but only if the water has actually come into contact with the atmosphere. And so this is to kind of give you the effect of like what happens underneath ice in particular when you don't actually have direct exchange with the atmosphere and some of that sort of disequilibrium that we get. So overall, what you see is this sort of similar behavior between all three tracers. Generally, ventilation age is closer to carbon-14. And then, but there are major differences between the carbon-14 and both ideal age and ventilation age. And that, of course, is because carbon-14 has this full-blown surface reservoir age effect, which because it takes a really long time to equilibrate with the atmosphere. So if we think about carbon-14 as a circulation age, plus a reservoir age, and plus some sort of residual that's associated with mixing, we can actually get some sense then of what those sort of other two processes, how those other two processes then compare to the pure circulation age. So this figure on the right is just a ratio of ideal age to carbon-14 age. And so these are depth versus time profiles now of those same regions. And what you get is that, yeah, in some time periods, you're seeing this relative match where you have these greener colors where ideal age and carbon-14 age track each other well. But there's plenty of other times and different depths as well where, you know, this reservoir age effect and potentially this residual as well kind of strongly impact the carbon-14 ages that you see. So this kind of helps you figure out what you're actually measuring when you're comparing to these proxy records. So nevertheless, though, if you actually do want to use carbon-14 age purely as a circulation age tracer, a really simple way of doing that is basically just, and you can do this in a model, that's the glory of having a model is that you have, you know, time points everywhere. You can do this by basically subtracting the ages of the source waters from some other region, basically. And so an example of this is in the Southwest Pacific and the deep Western boundary current. We know that the waters generally come from the deep Ross Sea. So if you subtract the ages of those two things, you can get a sense of what the actual changes are over time. And so now what you see is that all three of these tracers actually track each other pretty well. Similarly, you can do this in the Northeast Pacific, where you just subtract the deep North Atlantic age. This is averaged between 2 and 4 kilometers, which is more or less where you'd expect to have North Atlantic water coming in eventually as Pacific deep water. And so it doesn't match perhaps as particularly as well because there are other water masses within that region or other type waters that come from different places. But again, you can kind of see this similar behavior across the models. So just to conclude, so despite we have these mean state biases, this model generally captures the carbon-14 age variability that we see in some of these sediment core records. It certainly doesn't capture it in all of them, but it is pretty, I think it's pretty interesting given that this is a fairly low resolution model. And then this carbon-14 age itself, if we can really tell that it reflects this circulation age and this reservoir age change now. And we can use this model to do a lot of different and interesting analyses as a result of having all of these sort of tracers and all of these things actually wrapped up within this long-term simulation. So really exciting. CA-Trace, the output is actually now publicly available. There's a data set has a DOI, and if you want to learn more about it, you can visit the CI-Trace website here. So I will leave it at that. And I think I blew through that at an incredibly blistering pace.
Well, everyone's, I guess if, with your permission, everyone's talk is going to be posted eventually. So if there's details people missed in any talk, and I'm not just pointing at you, Hannah.
Yeah, that was
all of these
speedy.
talks go really fast for me because I'm trying to juggle different things, but they're all going to be posted on the website. So we can refer to, look at them later and.
Yes, they'll be there. You can talk to me about it.
And so this was do we have enough time for, question? This was an ocean forced experiment. And do you have any feel for how that might have impacted any of these results? I know you used atmospheric forcing from the trace simulation, correct? Yeah. If this be run with coupled, would there be any? I guess I know the carbon tracers are forced anyway from the atmosphere, but
yeah, I think it does actually impact like the eventual carbon values in the deep in the ocean, just because you kind of have to. Ocean isn't really allowed to the circulation isn't actually allowed to come in talk to the atmosphere, right? So that's kind of the biggest thing. And even if you force it like that, you can sometimes actually then lead to values that I think are lower than what they should be otherwise. So there is some bias with that. I do think a fully coupled simulation, in all honesty, would be the best way to go. So if we ever get these things in through the atmosphere and in the land model, I think that would be most ideal. But this is a good first step. That's the goal, right?
That we hope to be able to do.
Right. So this is kind of the interim step, which is like, all right, just force it with that. I do know that for the most part, the model ocean actually, the ocean in this model does track I think the temperature and salinity pretty well compared to trace 21, but I know that there are some biases because they have to do a lot of, I think, surface restoring just to kind of get everything, and pretty strong surface restoring, I think, and particularly in the Nordic seas and stuff like that. So that might eventually lead to sort of differences between the two simulations at the end of the day. So.
I do see Andreas's hand raised, but we probably need to move on to the next speaker. So maybe if you can ask your question in the chat, Andreas. So our next speaker is Qinghua Ding. Who's a researcher at Santa Barbara.
Yes.
And
okay.
He will be speaking on a multi-decadal scale, tropically driven global teleconnection over the past millennium and its recent strengthening.
Thanks for introduction. And this is Qinghua. And so the talk I will present today is the work led by my student and did with my co-worker and colleague from a different institute and university in United States and China. And from the topic, you can see the main idea is the time scale we try to focus on is the past 2,000 years. And we focus on some data is called last millennium reconstruction or reanalysis, LMR data version 2. And the goal is to understand circulation change over the 2,000 years. And we try to understand some of the role of internal variability like the IPO, interdecadal Pacific oscillation, how does the tropical signal or tropical forcing drive a circulation change over the two pole or two hemisphere over like the multi-decadal time scale. And also to compare this like recurring mode with the recent 40 years of variability. So this is the main goal. And another thing I like to draw your attention is that if you look at this panel here, this is from the 3 levels, or it's a linear trend and using annual mean data and Z200 as means the 200 millibar height, 500 millibar height in the middle, and the surface temperature. And this is the 3 data site, ERA5, and this is a SEMI5, a large ensemble, historical run, and mainly reflects the historical, the CO2 forcing, a response to CO2 forcing. Another one is a large ensemble, many model. Each model have a 40 to 100 members. So add them together. So CSM1 and the GFDL model and other several model, add them together. So the idea here is that if you look at this map, you find some discrepancy, but there's also some similarity. The similarity is the global warming signal warm everywhere, and in the model is tend to give a really uniform change everywhere. Like the in the model here is like the height change is has a maximum in the tropics, but in the observation, if you look the same variable, same pattern, same trend, you don't find at least a maximum in the tropics. And if you look the surface temperature, you find that there's some we call a non-uniform feature, that's like the maximum warming over the Arctic and a little bit cooling around the Southern Ocean, and no change over India, Eastern Pacific. But the model give us like the CO2 falls in favor is the El Nino-like pattern, El Nino warming. And so we think there's some mismatch or like the discrepancy. We try to understand why is that. We think it's due to internal variability, because we know the model can get this Arctic amplification due to this CO2 or like the positive feedback there. But the problem is the maximum warming, like the height change is not the maximum. Has no maximum over the polar region. It's the maximum height rise over the tropics. But in the observation, there's like the co-located between the two circulation, the two variable in a different level. So this means the maximum height rise in the Arctic, but also maximum surface temperature in the Arctic, and the cooling here in the surface, but also the lower of its potential height in the southern hemisphere. So this means that the dynamic behind the two warming scenario is a bit different. Something maybe due to its internal variability. So we think this is probably due to this like a tropical faulting or something related to the IPO. And this is a very simple plot as this one from observation. We just simply remove zonal mean component from something like this, but shorter period, because this is the internal mode, and the internal mode have some like the upper peak period, like the upward trend from 1979 to 2013. So it's just simply remove the zonal mean component from this variable. We can find there's a very clear tropical driven, like a cooling driven, like a geo pattern propagating to the two hemispheres. So favor warming over the Greenland and Arctic, and the favor cooling over Southern Ocean. So this is probably the reason to explain this asymmetry between this the polar change, like the Arctic maximum warming, or called AA, or something like the no change or Southern Ocean or close to Antarctica. So this is the main idea. So this is the reason for the years we want to see this is the how the similar mode behave over the past 2,000 years. So we looked at some like 2,000 years data. So before that, we simply calculate UF like using the recent 40 years. We find that this mode is a leading mode in a different level, just like to show like Arctic warming corresponding to Southern Ocean cooling, and all connect to like the tropical cooling. So it's more like an IPO signal. So we call it, so we give a name. It's called IPO BT. So IPO means IPO related bipolar teleconnection, something like that. And so this is from another paper, just to show a very typical IPO mode. So this is just the opposite sign. So there's the classical IPO pattern. And so now we looked at this LMR data. So LMR data is the reconstruction data, combined model, CESM4, 1,000-year simulation with some proxy data everywhere, just like a globe in globe. And things that proxy data is a more is available, is a more intense over like a northern hemisphere. So we looked at UF, just a simple UF for the southern hemisphere for this variable in this domain, and for 2,000 years, we find a similar mode. So this is the UF, like UF2. The UF1 is like a PNA pattern. So in this data, it seems like there's a cooling here, favors a warming Arctic, and some low pressure over here. And we're also using this time series correlated with the original proxy data almost everywhere. So we can see over 2,000 years, we can find a similar feature, like a cooling over the Eastern Pacific, or IPO, like a cooling phase or negative phase, corresponding to like the Arctic warming and the Southern Ocean cooling. And if you put a polar projection, you see most of it's ice core data, like a proxy data, clustered around this Greenland. And this triggering data show like the Eurasia cooling, okay, in just out of phase with this Arctic warming. So people call this like the warm Arctic cold continent pattern. So it still seems like it's not very new, just occurred recent 30 years, probably had occurred many times over the past 2,000 years. So this is the idea. Another one is simply using this proxy data, the coral data represent the tropical forcing correlated with the other like a coral other proxy data everywhere. So still can find an out of phase connection between the tropical forcing with the Greenland, but the same phase with Eurasia, like a trillion data. So last question we would like to ask, how important is the CESM4 to generate the signal? Probably everything we see here is simply due to the model itself rather than just the proxy data. So we just are using the original CESM4 data, like just 1,000 years of free running without assimilation, simply calculate UF. But we find UF, no UF very similar to this observed this teleconnection. But we try something, mix them together to see if we force this model to capture this mode, we still can get some of them. So we find half from UF1 and half from UF3, add them together, we can get this similar mode, like teleconnection, just like the cooling here and the article warming. So this last slide, if we put everything together, it seems like so this is observation, not observation, like a reconstruction data. So it seems like warming, cooling, and Eurasia cooling. But a model, if we're using this reconstruction, we still can get similar mode, like a cooling, warming, cooling, but it's pretty weak. So and just a time series with this mode, it seems like there's a lot of interdecadal variability, but the model itself give really like noise and pretty random randomness feature. So I think the main conclusion is this mode is probably real, and but it's the main sources for this mode is come from two. Okay, it come from two. One is a proxy data, but another one is a CESM4. So you can think like this is like make some like the dish, and this proxy data just like a seasoning, and but ingredient is mainly come from CESM4. So that just to prepare, set up this table, set up this ingredient, but the proxy data just changes the flavor, something like that. So so I want to stop here and take any question attendee may have. Thank you for your attention and. Yeah, listening. Hello? Oh, I cannot hear anything. Hello?
That's because I was muted.
Oh.
Thank you, Jinghua. I think we should keep moving, and looks like the chat has, I don't see any questions pertaining to you, but let's put them in the chat. And move on to the last speaker, Olivia Truax from the University of Otago, who's a PhD student there in New Zealand. And she was here. She's still here? Yes. Olivia, are you here? Here we go. You seem to be muted, even though it doesn't look like you are. We don't hear you. She may be restarting Zoom. There she is. Okay. Can you speak, Olivia? Don't hear you. Sometimes I find that if you go to the Zoom preferences and look at your audio and choose the correct audio. So I have like a screen and then a laptop, and you have to get the correct audio. And she probably can't see. She's not here. Let's just wait a little bit more. Let's see if she's emailing me. Okay, let's see.
I'm back. Can you hear me now?
Good.
Is that working?
Yes. Yes, it works.
Okay. Yeah, my camera decided to, anyway. I will try to share my screen.
Yes.
Okay. Success?
Yes, good.
Great, thank you. Okay, thanks for bearing with me, everyone. Hi, my name is Olivia Truax, and I'm a PhD student at the University of Otago in New Zealand, as Esther mentioned. And I'm here today to talk to you about my research reconstructing past Antarctic climates using paleoclimate data assimilation. And it's actually really exciting to be following Qinghua Ding because I'm talking about a lot of the same set of observations, but from the perspective of a geologist. So high resolution proxy records from the past 1,000 years are an essential source of information to augment the instrumental record. Of particular interest are the Little Ice Age, or LIA, thought to have had relatively cold global temperatures, and the Medieval Climate Anomaly, or MCA, when North Atlantic temperatures were warmer. These two periods are often used to explore past behavior of climatic phenomena, and though they were originally identified as warm and cool events, regionally specific temperature and precipitation changes between the MCA and LIA point to a potential dynamical origin. Several last millennium paleoclimate reconstructions indicate colder tropical Pacific conditions and a persistent La Nina-like mean state during the MCA, and a shift to a more El Nino-like mean state and an equatorward position of the Southern Hemisphere westerly winds during the LIA. Previous paleoclimate studies, including Crosta et al. 2021, which I've highlighted here, have hypothesized that changes in Antarctic surface temperatures and sea ice dynamics across the MCA-LIA transition are primarily driven by mean state changes in ENSO and the southern annular mode, which is the position of the Southern Hemisphere westerly winds. However, the limited spatial extent of paleoclimate reconstructions, particularly in the Southern Hemisphere, as you can see in this plot, really is a challenge to reconstructing making dynamical inferences using kind of these disparate reconstructions. And so here I examine the impact of large-scale modes of atmospheric variability on common era Antarctic climate using the last millennium reanalysis, which you were introduced to in the last talk. So the LMR is a paleoclimate data assimilation, which fuses the information contained in the proxy records, in this case, the Pages 2K proxy network, within the dynamical constraints of a climate model. Here, the CCSM4 past 1000 simulation. So changes in these simulated proxies drive the LMR, and then model covariance is used to fill in the gaps in time and space, which is particularly useful in the data poor region that I'm interested in, which is the Southern Hemisphere high latitudes. But so the results of a data assimilation can be productively compared to the last millennium climate simulations to assess the information added by the proxy network, because all the trends and the temporal structure in the reconstruction is driven by the proxies. And so this framework allows dynamical hypotheses regarding the impact of changes in large-scale modes of atmospheric climate variability, such as this one, to be rigorously tested in a dynamically consistent context. So my question that I'm trying to answer, does the LMR support a link between last millennium climate in Antarctica and multi-centennial trends in SAM and ENSO? And so just by starting off and looking at LIA MCA anomaly plots, the answer is kind of yes. So if we look at temperature and pressure anomalies and the regression between surface air temperature and mean sea level pressure and the NINO 3.4 index, we can see that last millennium changes in Southern Hemisphere climate in the LMR are characteristic of these large-scale mean state changes in El Nino Southern Oscillation. Mean annual temperatures in both the central and eastern equatorial Pacific are warmer during the LIA compared to the MCA, which is consistent with previous work suggesting a radiatively forced La Nina-like mean state during the MCA. So annually resolved climate fields actually allow us to identify the relative influence of changes in ENSO and SAM on last millennium climate in Antarctica because they have distinct signatures. So looking at mean sea level pressure and temperature anomalies centered in the Pacific sector of West Antarctica are consistent with tropical influence associated with a La Nina-like pattern prior to 1450 CE. So that's A up here on the left. However, this trend is pretty small. Note the change in color bar. And this makes sense due to the much lower number of proxy records, which are assimilated in the first part of the last millennium. So after 1450 CE, sea level pressure is higher in the Pacific sector of West Antarctica, so through here. And though this atmospheric pattern resembles the impact of El Nino, it's not strictly Pacific centered. The annular component is consistent with the pronounced negative trend in the southern annular mode during this time period and the combined impact of El Nino and SAM acting on surface in Antarctica. So after 1700 CE, the reconstructed SAM index is more variable and higher surface pressure in the Amundsen Sea sector of the Southern Ocean is characteristic of these kind of persistent, more El Nino-like mean state conditions in the tropical Pacific, while the southern annular mode is more variable in this latter part of the record. So I was interested in checking the LMR-based estimates of Southern Hemisphere last millennium climate against a complementary data set. So I further compared temperature anomalies in the LMR simulation in an LMR simulation, which excludes all Antarctic proxies, to an out-of-sample database of qualitatively assessed paleotemperature records compiled in Luning et al. 2019. And so warm anomalies are denoted by the red dots and cool anomalies are denoted by the blue dots. And both the LMR and these out-of-sample Antarctic records show a characteristic dipole pattern. After 1450 CE, most regions of Antarctica cool, while the eastern Ross Sea, which is just in here, and parts of the Amundsen Sea sector of the Southern Ocean warm. And good agreement between paleoclimate reconstructions using different proxy databases and really different methodologies provide support for the inference that these mid and low latitude teleconnections are a primary driver of last millennium climate in the LMR. So I went ahead and compared the results of the LMR to the CCSM4 to have a look at what the model prior was using or looked like. And the pattern of surface temperature and pressure differences between the LIA and MCA in the CCSM4 is notably different from that in paleoclimate records and the paleoclimate records and data assimilation. The regionally heterogeneous, dynamically driven pattern in the LMR and other paleoclimate records is really different from the global pattern of cooling in the GCM. A decrease in sea level pressure over the southern high latitudes or a southward shift in the southern hemisphere westerly winds in the CCSM4 during the LIA is consistent with an increased temperature gradient and polar amplification of cooling. But it's at odds with the precisely opposite interpretation from paleoclimate records, which suggests that the westerlies actually moved north across this time period. So the results of my analysis underscores that the CCSM4 doesn't simulate the low frequency dynamic climate variability that the geologic community infer from proxy records. In the LMR, assimilated proxies from the mid and low latitudes are adding new information about these low frequency dynamical relationships compared to unconstrained model simulations. And if we look at time series analysis, MTN analysis of the ENSO index from the LMR down here, as well as the CCSM4 and the CESM last millennium ensemble simulations, show shared significant periodicities in these kind of more high frequency ENSO bands, but the LMR also has significant low frequency periodicities that are absent from the free running model simulations. If we have a look at the NINO 3.4 index in the CCSM BOR, which is just down here, we can see that it basically just tracks global mean surface temperature. So it's responding to the forcing by volcanic solar and volcanic forcing rather than the type of multi-centennial dynamic climate variability that we get in the LMR. So to conclude, the results from the LMR support the hypothesis that low frequency tropical Pacific sea surface temperature variability played an important role in regulating surface conditions in the southern high latitudes during the last millennium, in contrast to GCMs. A couple of potential sources of bias in the model include the initial state of the ocean, which we've talked a bit about, as well as unresolved solar feedback mechanisms in the stratosphere. And I'll be really interested to see if updated solar forcing in CMIP6 might help to resolve some of these discrepancies. However, the LMR and other proxy records also have really important caveats, and I didn't have time to fully explore it here, but in particular, further analysis of the impact of changing proxy availability through time and how that might lead to spurious changes in the reconstruction will be really important to validate the LMR during the early part, especially of the last millennium. So more proxy records from the Southern Hemisphere and tropical Pacific that span the entire last millennium are going to be necessary to understand long-term climate variability in the Antarctic and predict its behavior in the coming decades. Finally, I'd like to say a big thanks to Betty and Esther for introducing me to the world of the CESM, and Feng Zhu for helping me get set up to run the fast implementation of the LMR. Thank you all as well for bearing with me as I got it together to present this talk to you. And I'd welcome your feedback and questions.
Thank you, Olivia. Yeah, I know you've looked at our last millennium ensemble. Did you do any comparisons to those simulations? You have a lot more. You can maybe reduce the effect of internal variability a little bit.
Yeah, I looked at across the ensemble and you never get the kind of centennial variability that the proxy records imply or have been interpreted to represent.
Yeah, okay.
And we had a look as well at the high top version of the last millennium ensemble to see if there might be something there in the solar, because there's a solar link between with the southern annular mode, and we didn't find anything there either.
All right, I think anything else can go in the chat, and we should probably move on. We do have another discussion. We're kind of running out of time before noon here, but I'm going to share my screen again because we put into the agenda some discussions for us to think about, or some questions for us to think about during the discussion. And I just want to open up the floor to anyone who might have something to say about anything that we've heard today or any other contribution they'd like to make. I do want to thank all the speakers for your great talks and for making this a great working group session with so much interest in submissions before we go. And then just open it up. The questions that we came up with for this discussion are: how can we better understand past climate changes through combining model and proxy? And then what do we need to do to improve the models? We saw a lot of indications that the models aren't getting everything right, but they are getting some things right. So let's open up the floor here for anyone who would like to say something. Any of the speakers who spoke just now on proxies, proxy model comparisons? I think one thing that seems, I know Clay in his talk, he compared to offline proxy models, which kind of helps translate model output to Proxies lets us do a better comparison.
Yeah, I mean, just on that, I mean, I think it was interesting, and you can definitely add uncertainties to the records with some of these forward proxy modeling.
Yeah.
But surprisingly, and stuff I didn't have time to show, is that even with really just simple assumptions about delta 18O precipitation and a temperature fractionation effect, the results were fairly similar. So it was like, I mean, basically saying that even if you don't have some of these additional models, you can still get a pretty good comparison, which was kind of comforting, but also a bit surprising.
It's good to know. I think what Olivia showed, how the models aren't necessarily getting our centennial scale variability in good agreement with proxies, and I'm not sure why that is. Is it that we're not we're dampening out these longer time scale variability modes of variability, or we're not getting it's part of the internal variability, they're not forced. Anyone want to?
I think Jessica has a comment on this.
Oh, Jess, sorry. Yeah, go ahead. Thank you, Andreas.
Yeah, I brought that up in the chat as well, but I think the bigger point is, so I think that data assimilation emerges a really cool way to, merge the model and proxy information. Obviously, that's something that, we've been working on too. But I do want to make the point that you really do need to be aware of what's going into those products, because, for example, in the case of the LMR, they just took everything and used a linear regression and put it in there. And so it didn't account for anything like proxy reddening, right? So proxy systems don't record the climate system faithfully in the spectral domain, right? They always redden it. And that could be, if you're a speleothem or drip water in your cave, if you're a coral, there's low frequency changes that may be biological. And so we now have more advanced proxy system models that try and sort of get at that, and they actually can be used in the assimilation framework and improve that. But we should always be careful about saying models don't have enough internal variability, because that actually, like, once you bring in the proxy symbol, the differences start to go away, right? Suggesting that it's really about comparing apples to apples and oranges to oranges. So when you're comparing proxies and models, you need to make sure you're comparing them as closely as possible, right? Before we make inferences about what's missing from the models. And similarly, like, in the case of the LMR, there's proxies in there that, there was sort of everything in the kitchen sink into it, right? And I would argue that when you're creating these hybrid products, you really need to have expert judgment about what is going in there, right? Because garbage in, garbage out, right? You put in everything, and then you're not really sure how to interpret what is coming out. So it sort of, to me, emphasizes a real importance, both with just normal proxy model comparison or with data assimilation, of making sure proxy people and model people are talking together and working together, because the proxy people have the domain expertise. They know these records inside and out, and they can determine the impact of that record might be on a data assimilation, for example, or even, they might be able to say in proxy model world, oh, well, that record has some things that we might consider from the original publication. And anyway, and so I guess it's just to say, to encourage people to keep talking to the proxy community and involving them in these studies, so that you have some expert knowledge on that front.
Good point. Yeah, I think tighter collaboration is definitely something that we could do better on. And
can I add to the discussion? Just
okay.
Because I think that's a good point that Jessica brings up, that there could be proxy biases, that lead to the reddening in the proxy record. So that could be one explanation. The other explanation, of course, could be in the models, that they're missing some low frequency variability. And I think we should remember that the models are still incomplete in the sense, for example, that they're not coupled into interactive ice sheets. So if there's ice sheet variability that could contribute some lower frequency variability, or maybe dynamic vegetation, I don't know. But there may be some issues in the models as well.
Okay, I'm going to go back to the hands raised order of things. So Olivia, I think, is the next. Olivia?
Yeah, I was just gonna say that I totally agree with all of Jessica's points. I am actually a geologist by training and came to the LMR as a way to try to generalize from these Antarctic records, because a lot of them were kind of point-to-point comparisons. And initially, I'd been really curious about how I could use models to interpret my records. And so, yeah, I would just agree with a lot of what has previously been said, and add that I think that, working closely with folks who know the proxy records is good and is also helpful, because I think that the proxy community can sometimes make these, point-to-point comparisons between individual records, which, aren't necessarily realistic given the climate system.
Okay, and then is it Qinghua?
Yeah, so I really appreciate the comments from Jesse. And great, the PSM is mainly emphasizes linear relationship. So I'm just wondering, anybody here or other groups have some interest to develop this LMR using like a machine learning method, because to try to using some more advanced method to take into account this nonlinear relationship. So I think that's maybe some promising direction to go further. Yeah, that's it. Thank you. Thanks for this.
And now Dan.
I'm sorry, I have a screaming child. Can you come back to me now?
Sure. Anyone want to add to this? Yeah, real life here. Anyone?
Will, Esther? Will Rush?
What? Will? Oh,
yes,
Will,
hi.
yes. All right.
I've kind of carved my niche in this sort of data proxy or model proxy comparison world, looking at hydrologic changes. And one of the things that I've noticed is, like, for modeling these regional scale variability, it's really important to have these high resolution models. But a problem I run into consistently is like the length of time that these models have been run for. Because I kind of question sometimes if, say, like 20 or even 50 years with like these high resolution data sets is adequate to capture sort of what could be like the sort of tail end of events that contribute to our actual observations of what's being deposited in response to hydrologic changes. And I mean, this is obviously a computational limitation, which would be really difficult to overcome. But I think it's something that would be important to address going forward.
Yeah, good point. Anyone? Dan, let me know when you're ready. Qinghua, do you still have your hand up? Oh, Dan, are you ready?
Oh, sorry.
See how long this lasts.
Oh, wait. Okay, go to Dan.
This is really interesting conversation. I guess, some of the things raised by the questions about, how to interrogate the fidelity of the model's representation of lower frequency variability, and, related to Andreas's comment, I guess I don't know what you could change about the model to change how it generates variability on decadal to centennial timescales. But I think moving forward with some of these data assimilation approaches, I would hope that those are some of the knobs that we might be able to turn on models to get them to better fit the data. I think, data assimilation like the LMR takes output from a model and then sort of stitches that together to represent each of the proxy years. But you're sampling there just from sort of how the model realizes internal variability. But we know that there's more to it, right? There's model errors. How do we sample model errors? How do we try to, correct more of the model? So I would, it'd be really exciting to think about running some ensembles or think about sensitivity experiments where, maybe in CESM, you're varying some of these parameters in past climates.
Mm-hmm. Will, did you want to say something in addition?
Oh, no, sorry, I can't get my hand to lower for some reason.
Oh, yeah, it looks like it went away. Oh, no, it's still there. I don't know how to do it either, so. I'm gonna stop sharing my screen because it hinders me with a lot of things. Okay, there we go. Oh, Arnie, is that you?
Yeah, I think important thing is that the models capture the variability. But what we notice is there's even larger problems. And so the models have some problems to capture the mean state. And for many studies we are doing here, the deep sea circulation, at least in the Pacific, is not adequately prescribed. I hope that will be improved in the future. I mean, we had in the past ocean circulation models where the deep sea circulation were well addressed, and that's always a problem if you couple the atmosphere with the ocean, that you get these ventilation inadequate seas. But I think that's actually a main focus, that we need to get the mean state of the climate right. And then we can focus on the variability of the climate.
Yeah. And the ocean, the deeper ocean might have more of a role in longer time scale variability as well. So yeah, it's you're right. We did have some of our previous models had a better, less sluggish deep ocean circulation. Okay, anyone else want to provide any sort of commentary? How are we doing with our, I mean, you know, we now have some geotracers in the model. They're expensive to run in every application. And it would be great if they were less expensive, but maybe the lower resolution configuration might help there to run more geotracers, but we're making progress there, but I suppose we have more progress yet to make before we're fully there. And then also with forward proxy modeling, data assimilation, all of these can really push us forward in understanding all these issues. So anyone want to mention anything about the models? What we need to do?
Well, I think
that enough other than getting better deep circulation in the ocean.
No. I mean, I think we need to also work with the tools, paleo tools, for the next generation. So when we are moving into CSM3, and and we need to also, some of the tracer tool needs to be imported into the next generation.
Yeah, and what I've seen with MOM is the current coupled MOM versions are a little bit even more sluggish in the overturning circulation strength. So I think they are working on that to improve it. I think it's getting better, at least. And the Ocean Model Working Group is having their session concurrently with ours. So we do have plans for in the next, in this allocation, we hope to be able to get some experience running with MOM to test out that coming CCSM 3 model before it turns into CCSM 3, give some feedback from the Paleoclimate applications on that. So Andreas?
Yeah, but Will was before me.
Oh, Will's having trouble with his hand. Did he?
No, I did have something to say actually this time. I did raise my hand this time.
Okay.
Yeah, I was gonna build off of what Arnie was saying about like the models recording mean states and extremes and trying to get the mean state right. And I feel like sometimes like when you do a deep dive in the proxies, there's a question of like what they are actually recording, not just hydrologic proxies like I was talking about earlier, but temperature proxies as well. And an example of this would be like Tex 86 and asking like whether this is recording actually a mean temperature, or is it more of the seasonal temperature? And so we should, it's just something that we should take into account when looking at our models, is it's not like our proxies aren't always recording mean states.
Andreas? Yeah.
Okay. I will, since, well, I will just state like again that I think the importance of a low resolution fast version is really important. I mean, we've seen lots of nice applications on high resolution modeling, and that's a nice thing too. But I just want to hope that people do not forget we need models that can run long enough, that include these capabilities of isotope and carbon cycle and so on. And so so for that reason, I think it's really crucial to have a working as low resolution as possible, I would say, version that you can use for these applications, for equilibration, carbon cycle, ice sheet coupling, and so on. And that would also enable more of the oxygen isotope ability. If we imagine the bulk of the paleoclimate data from the ocean, at least, is probably oxygen isotopes, and we have used only a tiny fraction of that data, LGM and maybe trace, but fully coupled oxygen isotope Earth system modeling that involves ice sheets, right? That because their effects on meltwater and so on, and affects O18, so it involves a fully coupled ocean atmosphere ice sheet vegetation carbon cycle model that you can run for these long time scales. So that's why I'm making this, keep repeating this plug for the low resolution model, even though I may sound like a broken record, but okay, I'll stop here.
Yeah, I think it's been something of a wishful hope, I guess. I'm trying to find the right words here, to have water isotopes in the ice sheet model. And I don't know if Betty can, Betty, you have your hand raised.
Well, it wasn't so much that, but just in general, both what Andreas just said and just put in the chat, and I think, part of, when you think of the water isotope version, ICSM 1.2, that was a community effort of very bright grad students and postdocs. So Jesse Nussbaumer and Tony Wong and Zhang Zhu all contributed to getting that going. And Jesse's still involved with CAM6. So that and the low resolution model, if this group could, got some really bright postdocs or students that want to work on this, if you can engage with the developers in land ice, ocean, land. I know that water isotopes is a big push, but all of this, it would be really great, even in MOM6, to make sure we get a resolution that works for us. Would be great to get the community involved. So we can help you coordinate that, get in touch, do whatever needs to be done.
Bill?
Yes. I'm just joining and I came in the middle, but I heard something about isotopes and ice sheets, and I was wondering if someone could fill me in on what the desire is.
To have to be able to track water isotopes coming off fluxes to atmosphere and ocean, land, coming from the ice sheet. So
to track the isotopes,
budgeting them, and then when there's a water flux, having an isotopic component that goes to the atmosphere, the land, the ocean.
So you're mostly talking about, well, you can melt ice at the top, or you can melt it when it flows into the ocean.
Right.
And,
So,
and if it melts in the land, that's when it still belongs to CLM.
Right.
But if you want to transport isotopes through the ice, that's a moderate, not a huge effort for the ice sheet model, because the ice sheet model is already set up to handle tracers. The bigger effort might be getting things through the coupler to the ice sheet model. So that's something I'd be glad to talk about if that's of interest. But it's something that we've talked about a little bit through the years, but we've never quite taken it through to completion.
Yeah, and it might require someone to really embrace the project and.
But Gunter and I could certainly help on the ice sheet modeling side.
Yeah. So.
I have a quick question. Since it seems like I was just curious while we're talking about the ice sheet, isotope, and all that. It seems like the land model is a roadblock, sort of, kind of here, and the same was like dynamic vegetation. So in the meantime, is it possible to like make a compo set with the ice sheet model with the rest of CESM, but maybe like a biome model connected? So you can do like dynamic vegetation. It can do like ice sheet interactions. And I know, or I heard that there's some effort on making maybe a box model for the water isotopes for the land. So I was just wondering, like, is there a benefit, like during those intermediate years, well, those more sophisticated things are developed, maybe we could still do science using a maybe simplified configuration.
I know Jesse is here in our list here. I don't know if he's on, but yeah, there's a simplified land model called SLIM. And it's been talked about as a potential place that a simple bucket model could be implemented, where you're just computing, you're sort of collecting the isotopic composition of the water and land very simply, and then computing the fluxes the way a bucket, I know Jesse, there he is, has used a simple bucket model in way back in his grad student days as part of CAM. There was a simple bucket model that you could turn on to before the isotopes were in the land model. Do you want to say anything or add to that, Jesse?
Yeah, sorry, I meant to contribute to this earlier, but I'm being one of those terrible, virtual people who is like half working. So my fault. Anyways, CLM in terms of isotopes in CSM2 is kind of the sticking point to my knowledge. It's not anyone's fault. It's just the people who are assigned to it are just really busy. But yeah, so there is a bucket model. There's a fancier bucket model that actually David Noon and Rich Fiorella developed for CLM5 for isotopes. So that gives you some of the differences of like transpiration versus soil evaporation and canopy interception, which are kind of the big ones. The catch is I don't know how, it's not going to do anything for snow. So if you want to look at like cold regions, I'm not sure how well it's going to work. But you can always add another bucket to the bucket model. So, and the advantage of this bucket model is actually all in CAM. It just needs the flux, this regular physical fluxes from CLM. So it should be relatively portable. Yeah, that's what I'm using for CAM6 because CAM6 has to run with CLM5. So I need a bucket model to test the isotopes in CAM6.
But you can verify that the water isotope tracers are in CAM6.
Yeah, they're in a developmental version of CAM6.
Yeah, not ready for release, but.
Yeah, but if you're like dying to use it,
okay.
I'm happy to share. In some ways, the more eyes, the better, because I haven't really done, basically it runs and it passes the eye test, but I haven't done any sort of like rigorous quantitative validation yet. So it's kind of use at your own risk, but whoever is interested on this call can use it if they want.
Great. Thanks, Jesse.
Thanks.
Yeah, sounds good. What about, I was wondering, what about the biome? Is there any kind of composite that could couple like biome to ice sheet and the full CESM, the rest?
Not to, no, I don't think so. The way that the biome vegetation data sets are input, it's kind of run in an offline mode. So, so climate model information, you know, climatology is given to biome from the climate model, and then biome runs and produces a distribution of biomes now, and maybe potentially PFTs. That would be a slightly new development, but biomes, and then the biomes are transferred to PFTs, given some assumptions about what PFTs are in what biomes and how much of whatever. And then that's input in a data set, a surface data set, and then the climate model is run with that. So it's kind of a periodically updated. It's not like a, you know, it's periodically updated, not run in a coupled situation. So someone would have to take on that project, I think. Bill?
Yeah, I was just wondering, do you or Betty see a long-term path for either biome or, let's say, fates being, maybe fates makes more sense in terms of being part of the runtime flow, but I was wondering, does fates do what biome does? Is that a possible long-term dynamic vegetation model that would do what we wanted to do for paleo runs?
Let's see. I don't see, Sam Levis was here earlier. He worked on the old dynamic vegetation model. I think Fates is the newer version that is part of CESM currently. I think we need to get some projects going using it. I don't know of anything where biome would be brought in as a sort of an online component. I don't know of anything like that, but Fates is already in CTSM, but I'm not sure it's in production mode yet.
Yep. Maybe we should have a chat sometime with Jackie, Rosie.
Yeah, and Rosie gave a talk to our working group a few summers ago about Fates, and it looked really promising, especially for deep time purposes, because it kind of represents niches. So yeah, I think that's probably the long-term path for dynamic veg. And in the short term, we've been using biome in an offline way. And if someone is really good, wants to try to, I don't know about creating a comp set REN. I think that might be overstepping it a bit, because a lot of infrastructure would need to happen to have that work in a kind of a seamless way. Now it to get biome updated, it takes a lot of human interaction with everything. It's not automated at all. So
yeah, I mean, it would be good to even have more than one dynamic vegetation, given that we know from like Betty's talk, how strong, and Marcus' talk yesterday, like how big the influence is. So it'd be good to sort of have like a different dynamic vegetation turned on, and then you can see like almost do a mini ensemble to see what the simulation results might be.
Yeah, I agree. Clay. Anyone else? Are we in our informal lunch discussion period here? It seems like we've gone over. I think Stephanie's still here, but I thought she had to leave at some point.
I have to leave soon, so
okay. Yeah.
I just wanted to make sure I captured everything in all the recordings.
Okay. Yeah, I'm periodically getting the chat just in case. You never know.